Yeah, hello everyone. Thank you for joining us today for the AIAA Los Angeles section um, town hall meeting. We have a distinguished speaker talking a very important topic in space, and um, this is actually the part three of the lecture, but actually he has been speaking several times, and we always welcome him. But before that, there's some logistic, and we have because the exhibitor, but actually from University of Urbana Champaign, very top aerospace university, to say a few words about their program. But before that, I want to show first of for folks here in person, the restroom is right outside the door. If you want to go to the restroom, you need to wave hands to the librarian, so they can unlock the door for you. So let me get the microphone because if I'm facing one side, the other side might not be able to hear. Okay. So. And the other thing is there's a water fountain outside. Then there's some candies on the table. But don't try to keep the room clean. If you have a trash, I encourage you to use the trash can outside. Don't use the one inside. To make a thing more, more organized, so we can keep borrowing the room. You can see this is a very beautiful room. I'm hoping our speaker someday can come here. This is so beautiful, and you can enjoy the set. But online is perfect, and the Tracy can also come here at some point. So other than that, so I think I'm done for the logistics. And either way, again, if you are a member, please remember to renew. If you're not a member, please consider joining us. And we have also volunteering opportunity. So I don't want to take too much time from the Tracy exhibitor and also from the speaker. So I just want to say thank you. And for folks online, highly welcome. Again, this event is being recorded. And if you want to speak out, ask questions, please raise your hand. So we'll enable your microphone. So that's the process. With this, and we welcome Tracy from University of Urbana Champaign to say something about her and their program. So thank you very much, Ms. Elving. Thank you. Go ahead.
Thank you. Good afternoon. My name's Tracy Elving. I'm the Senior Director of Corporate Relations for Aerospace Engineering at the University of Illinois in Urbana, Champaign. I'm actually an alum of the department. I graduated a long time ago, and I spent well over 30 years building airplanes and jet engines in industry. And today I just want to take a few minutes. So thank you, Ken. Thank you to the chapter for allowing us to speak. We have an opportunity at UIUC that I want to share, and let me maybe give a little bit of very quick overview about our program. Within aerospace engineering, we have 1,000 students. We have about 750 undergrads. We have roughly 300 graduate students split between master's and PhD. We have research that spans everything from certainly aerodynamics. Typically, if you've heard or worked with UIUC in the past, some of its claim to fame is around applied aerodynamics. And we have been growing our space side of our program dramatically, because our incoming students, probably 60 to 70%, are really coming to the program because of space and the excitement around really what's a very dynamic part of the industry these days. And so within UIUC, we are looking to actually bring on board a professor of practice. These typically are folks that come out of industry that have a lot of in-depth knowledge, about how, in this case, we're particularly looking at space as the expertise, whether spacecraft, whether that's satellites, orbital mechanics, communications. But we bring them in to the department. They're really spend a lot of time teaching. So you'll develop curriculum, you'll work with students. In this case, a PhD is not required for this particular role. We'd like a minimum of a bachelor's. It can be in aerospace engineering, but it also can be in any of the engineering disciplines. From that perspective, you can see that it's really around teaching undergraduate, graduate courses. And for us, it's really focused on applied engineering. So a lot of times we think of academia as strictly around research. And these days, more and more professors of practice in really applied engineering is becoming much more prevalent from that perspective. This role is a full-time faculty member with full voting rights. So you have all the same privileges as a research faculty member. You have really a lot of autonomy from that perspective. You can really define kind of what you'd like to do, whether you'd like to focus more on research, whether you'd like to focus more on applied applications, working more with industry, so on and so forth. So if for anyone who has not been around academia, so I spent all my career in industry, and about a year and a half ago, kind of as my last hurrah and give back, going to academia. And I must say that the opportunity to influence that future generation and know that they're the ones who are going to actually continue to move the frontier forward is really exciting. They're filled with wonder and excitement and questions, and there's nothing better than really helping them further that from that perspective. You can see just some of our students here. You can see that we kind of occupy a very big lecture hall with all of our students these days. Here's our faculty, and you can see in our different kind of areas the faculty that we have. Jason Merritt happens to be the professor of practice on our aviation side. We had a professor of practice who has moved on the space side, and that's why this role is open. We'd actually love to hire a couple in this area because our department's grown so quickly over the last 5 years. We are getting close to doubling our size from what we were in a very short time from that perspective. Okay. I will take any questions that anyone may have. You can see the QR code if someone's interested. We would encourage anyone interested to apply from that perspective. If someone has questions, I'll certainly take those questions.
So any question for folks here? But by the way, for people come late, actually Tracy from University Urbana Champaign Aerospace Engineering Program, they have a professor in practice a position open. So anybody you know interested, please let them know. And we do have a industry people here, so we'll definitely let them know, about this great opportunity. Yeah, it's wonderful.
Absolutely. Feel free to use the QR code.
Okay.
If someone has questions, you can see Rovi at illinois.edu. Josh Rovi is the faculty member heading up the search committee. You're welcome to email him. You also can email me. My email is Tracy, TRACYME at illinois.edu, and we'll answer any of those questions. If if for some reason you know someone or there are people that you think that we should network with around this particular opportunity, we would love to have that introduction as well. So please don't hesitate to contact us as we look to really fill this important position, and really be able to provide the best education to our students. So thank you so much for the time. I truly appreciate it.
No, the great pleasure, and we really love to connect. Finding opportunity for both sides, either side, for hiring or want to be hired. So we have been trying to do our best, and we're so glad you are with us. To tell a little about you and your program. That's wonderful.
Absolutely. I actually am an AIAA member and
Wow,
I,
wonderful.
I
Happy.
sit on the guiding coalition on the aviation side. So,
Oh, I see. I see.
um, so I firmly believe in the mission of AIAA. So, I will let all of you go on to your meeting. Thank you so much for your time.
Thank you so much, Tracy. Yeah, stay a few minutes, and Dr. Gary is also our member. He's our Edward Fellow. And I'll say a few words, and then you'll listen to what he said. Very interesting, his career. Okay, so thank you very much for Tracy. It was wonderful, and it's good to have you homecoming to AIAA. So we'll stay in touch. Thank you. Okay, so Dr. Gary is ready there. So basically, as you people know, and most of you in LA and also work in the industry can understand this space environment is something very important. And that's why the LA section, we've been putting multiple events for years on space weather, space radiation, and electronics packaging, and space medicine. But things are kind of missing, what is physics behind, and what is what's it really involved. And we have Dr. Henry Garrett as our AIAA fellow. He was become the fellow in 2019, and he got the AIAA James Van Allen awards. As you know, Van Allen is very big, space, Van Allen radiation belt. So those kind of things. He got a award in 2022, and he retired from JPL 2023, and I've been in the industry for 43 years, and you've been with start from Korean Air Force, and he has a long history. He also got in early career, even when he was start with doing spacecraft charging, and he was already awarded, for outstanding contribution and performance at DoD, and he was like become NASA the most valuable employee. It's just highly decorated and very knowledgeable. He knows top and down in this field. He got a degree from space physics. And if we talk about space environment, he's the guy to go. He's an expert to go. And he authored multiple books, including the one you saw in the bio, and another one with our new president, Dr. Hastings. By the way, I have a copy of that, and it's a very good book. And I encourage everybody to look into his publication book. He has over 150 publications, and is really world expert, and is hardly sought by all the community, domestic or international, and everybody just want to learn, from him about this very important, exciting field. So he will talk more about his career, very exciting, lots of humor. So I don't want to cause any further delay. So let's welcome our distinguished speaker, Dr. Henry Garrett.
I think Tracy has to cut off her sharing.
Hello?
Yeah, I think Tracy has to cut off sharing.
Oh, Sherry, are you still sharing? Tracy,
I turned sharing off.
Well, I don't have it. Well, let's see if I can make it work. All right, let's see. Okay, let me see if this works. And let's
Yeah, we can see you. We can see you.
Okay, is it full screen? I got to get back to the beginning.
Yeah, it's full screen. Yes.
Well, there you go. You've had the entire lecture. All right, my name is Henry Garrett. I had a 30-year career as an Air Force officer, ended up as the head of all the reservists and the Space Command down at Los Angeles Air Force Station. And I ended up as a colonel in the Air Force. I retired after 30 years. And simultaneous with that, I overlapped with my career at JPL. I started in 1980 at JPL after transferring from the Air Force to reserve status. I went to Rice University for 8 years in the space physics department there and got my undergraduate and PhD in space physics and astrophysics. I guess the only other really interesting thing about me is I grew up in a small town in New Mexico called Roswell. I was actually born 9 months after landing that took place nearby, if you remember what Roswell is noted for. By the way, the mayor of the town and the other principals have come to my house when I was back visiting and asked me never to tell you what actually happened in Roswell. So do not ask. I can't tell you. Anyway, the bottom line is that I grew up near the Robert H. Goddard Museum. And that was the first spaceport in the United States was at Roswell. And back in the 30s and 40s, he did hundreds of launches from there. And I grew up, you could go, I met Mrs. Goddard, I met Werner von Braun, and all those people used to come regularly to Roswell when they opened the museum and such. So I got early on exposed to space. My father was an Air Force officer also, and he was navigator, so I was exposed early on to astronomy. Anyway, our talk today is going to be on the spacecraft environmental interactions. The other two that I've already given are on other aspects like radiation and and spacecraft charging and other types of interactions that I'll be discussing. Today, I'm going to concentrate primarily on atmospheric and ionospheric effects at low altitude orbits, and in particular, things like shuttle glow, oxygen erosion, things of that nature. So let's get started. Following my introduction, I'll discuss why we care about these environments. Then we'll discuss the environments themselves for Earth, the outer planets, and the man-made environments. And finally, we'll conclude with discussions of effects of drag, contamination, surface damage, glow, plasma interactions, and similar effects on in the ionosphere and atmospheres of the various planets. So, bottom line is an ounce of prevention is worth a kilogram of cure. You may notice the allusion to kilograms and ounces. That's because I was involved with one of the Mars missions where we got meters and feet mixed up and managed to crash into the planet. So you have to be very careful about your units, as you'll see as we go through here. The bottom line, though, is that spacecraft are continually growing in complexity and their sensitivity to the environment. To give you some simple examples, oxygen erosion will eat away silver. The Japanese launched a satellite where they used silver interconnects because that's a very useful material to use. But it was at very low altitudes, and the effect was to basically dissolve the silver interconnects. I had a few discussions with them about that. As you'll see as we go through here, it's these second order effects that can be overlooked very easily, and particularly for the CubeSat regime. And you need to think about all of these problems. Most of them won't be that critical for you, but things like oxygen erosion and drag can be detrimental to your mission, as we'll see. The bottom line is this. We come in with environmental models, we make environmental estimates, and from that we do environmental design requirements. That is how to prevent the effects of that particular environment on our system. The issue though becomes very quickly, do we test for it or not? Bottom line is you should always test, but you can over-test. And a lot of the projects that I've worked with simply do not want to do the type of testing that we require. If you under-test, then you can have design failures. To give you an example, they took the Voyager spacecraft and they arc tested them to see if they would fail. Sure enough, they blew out the central computer on the engineering model of the Voyager. As a result of that, I was hired. That was the reason I was brought to JPL, because of my expertise in spacecraft charging. And they redesigned the Voyager spacecraft to correct for that. As it was, when we went by Jupiter, the spacecraft charging did occur, and there was arcing, and it reset a few milliseconds every time there was an arc. There were 42 arcs on Voyager 1 as it went by Jupiter and its radiation belts. The net result being that every time the spacecraft was reset, the science computer, as opposed to the mission computer, the pictures that we were taking of Jupiter slowly shifted out of the view. So by the time we left the planet, we actually were not getting pictures of Jupiter, or at least they weren't very well centered because of the shift into two clocks. So you can never over-test, I believe, although the fact that they blew out the computer during the testing at least led them to put a lot more protection in. Even so, we overlooked some of the more subtle effects of spacecraft charging, and they missed it. So you can under-test and you can over-test. And that's the real critical issue, particularly with these new generation of CubeSats. CubeSats offer a very critical problem for the user. If you only want them to last a few weeks or a month, then you don't worry about it. But if you're going to want them to last for months, then you're going to have to start considering some of the effects we're going to be talking about today, because they can turn out to be major effects. This is the process I want to describe to you that I like to follow, that I push for my projects when I am given a mission to consider. On the left, you'll see the environments that I consider important: neutral atmosphere, electric and magnetic fields, electromagnetic fields, the solar wind, ionosphere, aurora, trapped radiation, galactic cosmic rays, solar proton events, meteoroids, and debris. Across the top are a number of the types of interactions that you have to consider. Obviously, dose, single event upsets, latch up, surface charging, internal charging, plasmas, wakes, power loss, V-cross speed, surface damage, contamination, glow, particle impacts, torques, and thermal. And then what I always suggest doing is taking the environments that you're going to be experiencing for your mission on the left, as you go across the top, mark for your mission what you think will be the important ones. I marked here in yellow the ones that will be considered here in this talk today. You can see that surface contamination, damage, and glow are some of the issues that I'm going to be considering for the neutral atmosphere. The ionosphere can cause surface charging, plasma wakes, and power loss, as we'll see. Similarly, the aurora can cause charging and can also cause weird plasma effects in the sheath. Finally, the ionosphere. Finally, we're going to go through all those different types of effects. Now, the second step in that process is, once you've got the interactions that you need to be considered, there are a bunch of options that you can take to affect the design of your spacecraft. For example, with power loss, you can put shielding, insulate it. You can change the position of sensors and such if they're in the wake as opposed to the ram position. You can alter the shielding for contamination. You can put baffles, things of that nature. Similarly, positioning, you can move for surface damage, you can move surfaces that are successful, sorry, oxygen erosion, you can move them out of the ram direction. Contamination, if there's a thruster that's firing, you can move it so that you're not in the direct flow field. Similarly for glow, as you'll see, you don't want an optical sensor that looks across a surface that's going to be repeatedly glowing in the dark. Material properties can be altered to affect surface damage and contamination. Finally, grounding for surface charging is a major issue. Plasmas, you can change the trajectory so that you're higher altitude, so it's not as big an effect. Perhaps for surface damage, you can again change it so that you're not in orbits that are polluted with orbital debris, things of that nature. And similarly for glow, you want to get up high enough above about 800 kilometers so that the surfaces don't periodically glow. Operational procedures can be changed. I'm sorry, I keep getting these calls. You can do the operational procedures to change the contamination and glow effects. And finally, construction techniques. You can put extra shielding, things of that nature. So that's the second step. The third step is you need to consider what the effects on your design will be from a cost, weight, power, complexity, reliability, availability, usability, and special issues. By the way, I'm going to stop for 1 second and put this on airplane mode. Let's see, how do I put it on airplane mode? Yeah, I don't know. All right, I guess, here we go. Airplane mode. Okay, that'll shut the phone off. And for example, cost. If you have to put shielding, it can be very expensive. For positioning, again, cost. If you have to move things around materials, you have to maybe use tungsten instead of cheap aluminum. The complexity, it'll add to the complexity. So you begin to get the idea. So I see how you design a spacecraft and evaluate it as a 3-step process. Environments versus where you're flying and the effects. Then the methods for ameliorating those effects. And finally, how those effects will have on your cost, usability, things of that nature. So anyway, that's my process. We'll talk about that later again too at the end, but I wanted to remind you of how I think these things fall out in our process. Next thing, these are the environments that we're going to talk about. Obviously, Earth is going to be the main one, but we're going to be looking at Mercury. Is somebody talking? Mercury, Venus, Moon, Mars, Jupiter, etc. We're going to be looking at these. Somebody's talking anyway. Now, how do we describe the environments? Well, the simplest way we do it is we usually talk about a distribution function. This is a sample of a distribution function for the plasma. It's called a Maxwell-Boltzmann distribution. The key parameters here are the mass of the particles, the number density of the particles, and their energy. That's the KT in here, 1/2 mv squared over KT, where T is the temperature of the plasma. Anyway, there's different distribution functions, as we will see as we go through here, for the atmosphere, for the ionosphere, and for the plasmas, and for their effects. Actually, there's similar ones for the space debris environment and things of that nature. Those were covered in some of my earlier talks. So moving down, what are the things we care about? We care about the number density. That's the integral. If you integrate the plasma distribution function over the velocity space, you'll find that you get, you'll rederive the number density. If you do it again with multiplying by the velocity, you'll end up getting the number flux. If you do it over velocity squared, 1/2 mv squared, you'll get the energy density, and ultimately the energy flux is at another velocity. So it goes 0 velocity, basically integrate over the plasma distribution function, which is a function of velocity. And then you integrate it over first order velocity, second order velocity, third order velocity. You'll get those 4 numbers. And those typically are the main things that you need to know about the space environment. Is the density of something, the flux of the particles, the energy density of the particles, energy flux. And you can rederive the temperature by dividing the energy density by the number density, or the energy flux by the number flux. You'll notice that there's a ratio of 2/3 and 1/2 in there that are necessary given the distribution functions above. So this is very critical, that you need to know how the particles are distributed in space and velocity. Now, here are the two of the main environments we'll be talking about today. On the left is the ionosphere. You'll notice the weird shapes, the layers, the E layer, the F1 layer, the F2 layer, etc. There are a number of different layers associated with the ionosphere. This is as a function of altitude, this is the electron concentration. On the right is the atmosphere. Now, I want you to notice one peculiar thing. Up to about 100 kilometers, the atmosphere is very thoroughly mixed. The collisions between the particles are sufficient to mix the particles. And so it's basically 80% nitrogen, 18% oxygen, and then all the other garbage, as you can see up there, oxygen, mono atomic oxygen, O2, N2, argon, hydrogen, and helium. And you can see that the atmosphere goes basically from nitrogen dominated to oxygen dominated to hydrogen dominated at very high altitudes. We're going to be looking primarily below 1,000 kilometers and above about 100 kilometers as shown here. Now, we'll discuss in the next couple of slides how you get these types of curves, because they're very basic to the way we modeled the atmosphere and the ionosphere. Let's look first at the atmosphere. Basically, you remember your PV equals NKT. That's the standard formula for pressure, volume, and temperature relationship. If you take and divide the volume into the total number of particles, you get a number density. So we're going to change from pressure equals number density to NKT. And then you move it again, where we're going to do the substitution. N equals P over KT. Now we go down to the next step. The force on a cube of material, a rectangular cube of material, is the change in pressure from the top of the to the bottom of the cube, and the change in force is force. Since pressure is force per unit area, you're going to get the force change in force divided by the area. So that's pressure times area equals the force, obviously, or as we normally think of it, the pressure is equal to force per unit area. That's what A stands for. Now go to the next step on the right there. Now what we're talking about is we're going to convert the force into typical units. For example, let's say we have a single species as a mass 0, m sub 0. Then there's a number density of the particles, and then there's the gravity constant for acceleration, and then the area and times dx. Area times dx is the volume. You multiply that by the number density, you get the total number of particles. You multiply the total number of particles by the mass of a single particle, and you get the total mass. And then you multiply mass times gravity, and you get the force on the particles, the dF. Hopefully that's straightforward to everybody. If anybody's confused, you're welcome to ask me a question. Then we go to the right, we're going to take the number density and we're going to replace it with the pressure over KT. So that should be an obvious step. And so what we end up with is that the change in pressure is equal to the average mass of the particles times the acceleration of gravity times the vertical change in distance over kT times the pressure. Now we can integrate that. If we move the pressure over to the left, we get 1 over P times the change in pressure. We integrate that from the pressure at the bottom of the atmosphere to the pressure that where our satellite is or where our aircraft is. And you do the substitution from above. You end up with the pressure is equal to the pressure at the surface, E to the minus mgh over kT, h being the scale height, the distance over which above the ground that you are. And if you look at the right, you can see that below 100 kilometers, because the atmosphere is thoroughly mixed, because the particles have enough so dense that they run into each other and they stay completely mixed. So up to 100 kilometers, you have a fixed concentration, and you would take the mean weight of the atmosphere for that, 80% nitrogen atoms, 18% oxygen, etc., O2. But above 100 kilometers, the particles no longer manage to run into each other. And so the magic number is around 90 to 100 kilometers, and that's where space, quote unquote, begins. We find that the particle species are in diffusive equilibrium, and that's what you're seeing on the right there. So each species has its own temperature, though most of them have the same temperature, at least because they start at 100 kilometers with the same temperature. The particles then fall off with their mass, their mass and temperature. So that's what you see on the right. You also need to define the temperatures, we'll see a little later, for each planet. So you get a temperature curve and you get a number density curve or a pressure curve, depending on what you want to do measure. Because you can see that pressure is obviously equal to number density and in kT. And if T is constant, you get these types of curves on the right. So hopefully that explains why we have an exponentially falling off atmosphere. Below 100 kilometers, collisions dominate. Above that, each individual species reaches its own scale height and variation. Now let's look at this is what a standard model. For many years, the AIAALA model has been the base simple model for atmospheric drag. I worked with Luigi AIAALA, and actually I was his contract monitor for a number of years when he was inventing these models. And I used to go down, he did it on an HP 35 hand calculator. He did all these calculations. And up until fairly recently, in fact, I think they still use his models. Before he died, he gave me a model that included the effects of geomagnetic activity. I was able to pass that on to the people down at NASA in Huntsville. And you can see here on the right the temperature of the atmosphere, and on the left is the atmospheric density at about 400 kilometers. This is the altitude at which the shuttle was orbiting. If you look on the right, there's an interesting fact that you should be aware of. You're looking down on the polar cap in both cases, and you can see that the number density peaks at about 30 degrees, and so does the temperature. That's because it takes a while for the sun to heat the atmosphere, and as the Earth turns, as it turns counterclockwise, the density and temperature slowly go up, and that's why there's about a 2-hour displacement. 15 degrees is about an hour, so 30 degrees is about a 2-hour displacement before you get to the maximum heating and the maximum density in the atmosphere. I think that's a fairly interesting factor. And so your maximum drag and stuff is at 30 degrees, not at noon. So anyway, that's the way the atmosphere behaves. And these are a slice at 400 kilometers looking down on the polar cap for reference to give you an idea of what it looks like. And you can get some idea of what how many grams per cubic centimeter there are in the atmosphere. Now, let's explain why you get these so-called Chapman layers in the ionosphere as opposed to the effects of the neutral atmosphere. Well, we have to take into account the neutral atmosphere. That's the blue line on the left over there. As you can see, it falls off, as you would expect, exponentially. And on the right, you can see the UV radiation coming in. What happens is the ultraviolet radiation ionizes the atmosphere and creates the ionosphere. So as you come down, the UV is being absorbed by the exponentially increasing atmosphere. And so you get a break point at about 40 kilometers shown here, where you get this so-called Chapman layer. In other words, the UV is absorbed as with the exponentially increasing density of the atmosphere, and you get a layer in there. And there are various layers because of different chemistry and of the atoms, ionized atoms that are interacting with each other. And that's why you get the E layers, the F layers, the F2 layers. It depends on the composition and the chemistry for each layer. But you can see below 100 kilometers, everything's pretty copacetic. You get the one layer, roughly the E layer. And then as you get up, you start to get different combinations of ions, percentages, and so you break it out into these different, what are called Chapman layers. So that's the ionosphere, and that's why we see the layering in the ionosphere. Here's some details for you. By the way, this is a day versus nighttime on the left up there. Then we have the constant of electrons. Then we have the ion composition. And you can see that below 80 kilometers is basically nitrogen, hydrated ions, and stuff like that. But above about 100 kilometers, it starts to be O2 plus and O plus, as you can see there, and NO plus, and it gets very complex chemistry. At some point, it becomes hydrogen primarily. Then that's the daytime in the middle, nighttime on the right over there, and gives you a feel for it. And at the bottom, of course, I plotted the temperatures so you can see how the temperature for electrons and the neutrals, that's the neutral atmosphere, and the ions, how they change. So hopefully that gives you an idea between daytime and nighttime, how these things do. And one of the interesting things is at night, if you hold your hand up, it's never dark because the chemistry of the ionosphere is always changing, and you're getting light emitted by the different chemical processes. So like I say, if you go out in a really dark area and hold your hand up, you will see the background light in the coming from the ionosphere's chemical processes. Growing up in Roswell, I was able to see that quite frequently. I think that's probably the reason the aliens landed, because it was really dark. Anyway, this shows you the same thing as we did at 400 kilometers for the neutral atmosphere. This shows you where the ionosphere densities peak. Now notice that over the polar caps, you get an intense temperature profile. That's because particles can easily get into the polar caps from the solar wind and from cosmic rays, things like that. And the bottom line is that the upper atmosphere is heated over the polar caps. And so you don't get quite the same pattern as you do for the neutral atmosphere. And you can see on the left the complication. We'll show you more examples of that when we get to the effects of the ionosphere on communications. I have a whole slide on that when we get there. So now here's an interesting effect. When they launched the Skylab back in 1973, it was a Saturn V, and it happened to fire its main rocket engines right as it was crossing into the most sensitive part of the ionosphere. And it basically knocked out the ionosphere. It was basically a massive water dump, and it neutralized a lot of the ionosphere. And you can see the dip there, the black line on the left. And the measurements were made from Sagamore Hill up near Boston, when it's a Skylab path went through there. So what I think is interesting here is to tell you that you can make massive changes in the ionosphere if you want to. And there are people who would like to make massive changes in the ionosphere, particularly since the ionosphere can be really screwed up with geomagnetic storms and things like that. You might want to quiet it down so you can propagate a signal, as we'll see a little later. Now let's start looking at the planets. First planet, of course, is Mercury. This gives you some idea. It does have an atmosphere and does have a magnetosphere, because it has a weak, though interesting magnetic field. So it has a magnetosheath, all the standard things. And on the left, you can see the different species and how they rate for the atmosphere, but is not very high. That's the problem. It's like 250 particles per cubic centimeter at the surface, and so it's not much of an atmosphere. Venus has a huge atmosphere, but it does not have a magnetic field, and as a result of that, and this is very important, the ionosphere and atmosphere ionosphere in particular is crushed on the solar wind side. If you were to look at 400 kilometers, the ionosphere basically goes to zero as the ionosphere is smashed down. The surface pressure, by the way, is 92 bars. That's almost 100 times what the atmosphere of the Earth is at the surface. The density's significantly larger, and the average temperature is almost 800 degrees Kelvin. And it's enough to melt lead. And I think you can appreciate what that is mainly carbon dioxide. So it's very squished up carbon dioxide with just a little bit of nitrogen at the surface of Venus. So that gives you an idea of how the atmosphere goes off. It's basically CO2 at the surface. Around 160 kilometers, it changes over to oxygen. And in fact, there's some speculation that there may be a livable region in the upper atmosphere of Venus where we could float balloons and things. And there are even people who propose that there might be life there because of the switch over from oxygen, though I don't. They claim to have seen phosphor, which is supposed to be a dead giveaway for life. And there's been a lot of excitement over the last couple of years on whether or not life might be present. But I think that the observations have been called into question in the last couple of years. On the left, you can see the ionosphere, and it folds over at 400 kilometers. There is no ionosphere after that. And the solar wind pressure, of course, changes, and it moves up and down a bit. But it's a plasma of the solar wind interacting with the plasma of Venus's ionosphere, and it crushes the ionosphere in the solar wind direction and back and towards the wake side, it stretches out, and it's more like a normal ionospheric fall off. So ionosphere in the front smushed, the ionosphere in the back is a regular fall off. So anyway, this gives you an idea of what Venus is like. It's hellacious. Then this is the Earth system. This is the Earth's radiation belts. I'll be showing you comparisons of those just for reference. And this is a DMSP map that takes pictures of the Earth, and you can see the lights at night. Some of the interesting things, if you look over there by Japan, you can see the island, you can see Korea, and then between Korea and the mainland, South Korea and the mainland, there's nothing. That's North Korea. It doesn't have lights at night. So interesting. Anyway, that shows you the Earth. I can blow it up for you if you want. It got Moscow is the most lit up place in Russia, and it forms a cobweb pattern. And if you look down along the Nile, you can see the Nile in Africa. And if you look up to the right, you can see the flare off from Saudi Arabia and oil fields and such. That's not lights, that's the burning of the natural gas that they burn. Then this is the moon. The moon does have, at about 14 inches, has an atmosphere. And it is very insubstantial, of course. But by the same token, it turns out that when an astronaut walks, he kicks up enough dust that you can create an atmosphere. And is one of the interesting effects, as we'll see in a second, is that the edge of the terminator edge of the moon glows from a kind of plasma glow that's seen. You can see that that you get lunar surface charging. I did some of the first measurements of that, and you can see down at the bottom here where the magnetic field locations are. They're little spot regions of magnetic field, basically probably metal asteroids that crashed into the moon and deposited a large iron deposit that had a magnetic field with it. This is what we're talking about. The lunar dust consists of grains. Basically what happens is when a micrometeoroid or meteoroid or any kind of asteroid hits the surface of the moon, it vaporizes and crushes the material that's there. As a result of that, and I took a course in this when I was at Rice, and we actually got to study some of the samples. It looks like broken glass, very microscopic broken glass, because all each meteor comes in, hits the surface, meteoroid hits the surface, fractures the stuff, it produces gas or liquid that then turns into glass, falls back to the surface, and then that's eroded by all the little micrometeoroids hitting the surface. And you can see down here the enhanced dust cloud. Basically what happens is the dust becomes charged near the terminator when the photoelectron flux is emitted from the particles, and they dance on the edge of the terminator. And so there is actually a little dust cloud that reflects light. And the astronauts were able to see this in all their missions. The other thing that's bad about it is that this is ground glass. And the ground glass, when they wipe their hand across their visor, they manage to get scratches all over the cover visor. And you can see they had a real problem. They couldn't, if they tried to clean the dust off, they'd scratch the optical surfaces and couldn't see out. So that got to be a sandpaper type effect that's really bad. And in part it's because the dust is electrostatically charged. Then we go to Mars. Mars is a lot like the moon because of the micrometeoroids and stuff constantly hitting the surface and making this stuff called regolith. And the regolith powder is similar to the moon, is basically ground glass. And here's the atmosphere, the ionosphere and atmosphere of Mars. As you can see, at the low altitudes below 180 kilometers, it's primarily CO2. Above that, it's oxygen. And that's the problem. The UV ionizes the gas in the solar wind. Particularly the solar wind is believed, because there's no magnetic field at Mars, significant magnetic field at Mars, ionizes the gas through collisions with the solar wind particles, and you get atomic oxygen, and that gets swept away. On the left, you can see what the ionosphere looks like, as measured by Viking and theoretical. We now have very detailed models of the ionosphere and the atmosphere of Mars from the landers and from the orbiting spacecraft that you can use. But notice that, again, like Venus, there is no significant magnetic field on Mars, permanent anyway. And as a result of that, you get the smushed in ionosphere in the direction of the sun. And as a result of the no magnetosphere, the atoms get ionized, and the oxygen in particular and hydrogen gets swept away, and the water goes away. That's the current thinking, is that the water disappeared because there's no magnetic field to protect it. This just shows you the dust again. There's a problem though at Mars that we don't have at the moon. It turns out there's something called perchlorates. Perchlorates are basically used for rocket fuel, as I understand, or as bleach. And I know you saw the movie The Martian, and I love it. It's a great movie, but it never did explain how he got rid of the perchlorates, which would have bleached out the potatoes from the very beginning. Anyway, this at the bottom picture there gives you an idea of various models that people have developed of the dust grain size and density as a function of grain size along the bottom. Somehow I thought I corrected, but the scale on the bottom is missing. So notice that there's large disagreement for the smallest particles. And remember that the perchlorates, they actually have a device, I think it's on the Perseverance, where they can take the dirt and process it and get the perchlorates out and make rocket fuel for future missions. I think that test was actually run about last year or so and was very successful. So you can dig up the dust, make it into rocket fuel and fly home. That's the theory. So let's go to the next one. Jupiter, of course, is the biggest planet. There's my models. All these are my models, by the way, of the radiation belts. This is the radiation belts for the protons on the left, the electrons on the right. And you can see there's a significant difference in this intensity of the electron belts at Jupiter. If you're interested in those types of things, which I am. In fact, I did the models for Europa. The radiation models they use in designing Europa were my model, was this model. And at the last minute, I learned after I retired that they found out that some of the parts that they were planning to fly are ultra sensitive to radiation, more so than they thought. And so they're flying a box of sample parts. And as the parts decay, they're going to try to figure out what's the best way to turn on and off instruments to preserve the radiation sensitivity. At least I think that's what the process they're doing. On the left, you can see the ionosphere is highly variable at Jupiter. And on the right, you can see the atmosphere of Jupiter. And you can see hydrogen dominates pretty much H2. I think that, yeah, it's H2 and H3, I guess. No, I guess that's H2. I can't quite read it. I guess maybe it's N2. Anyway, H dominates above 600 kilometers for sure. I have to blow that up, I'm sorry. Anyway, that's the idea of the atmosphere, the density and all the different compounds and such, and ammonia, methane, things of that nature you can see listed there. Then there's interesting, it turns out that Europa has an oxygen torus associated with it that APL found. The energetic neutral atom imager was able actually to detect the neutral oxygen atoms in the middle picture, middle thing here is Europa itself, and then you have the if I remember exactly, those are the two lobes of the hydrogen and oxygen atoms with a fraction of oxygen or sulfur atoms at the same speed. And you get some idea that it's much more complex than people actually thought it was. And that there's actually a torus of oxygen. We did do studies to see if oxygen erosion was a problem. It wasn't, but I did have people make models for me of the oxygen environment, and we did run those against the materials that we were flying on Europa to make sure that they weren't affected by oxygen erosion. Anyway, this is Io, that's the inner moon, and you can see all the volcanoes and things of that nature. One of the more interesting projects I was asked to do was to estimate when they flew real close to the surface of Io, they went through a volcano. They were worried about how many rocks they would run into, and I did the calculations. Unfortunately, that volcano turned off. And then there was a much bigger volcano that suddenly came and erupted and hit them. They came real close to being fried. It was an interesting experience, apparently, for the mission controllers when they went by and they went through this volcano. So you can spitting up sulfur and rocks and things like that. Anyway, this is the Io atmosphere, and that I used for some of the calculations. You can see on the right the volcanic plumes and things, and the torus. There's a sulfur and sodium torus around Io, and that I modeled for them, and it is bright. It's actually big enough that you can see it, and bright enough that you can see it from the Earth if you use the right filters. Hubble shows it up very well. And I worked with a group that was measuring that, and it's quite interesting. You can actually follow the movement of the ring as the magnetic field controls it, because Jupiter's magnetic field is offset and tilted, and you can follow it flapping up and down as it goes by Io. Anyway, there's Saturn. This is the Saturn radiation belts. Again, protons on the left, 10 MeV, and 1 MeV electrons on the right. And you can see the comparisons. Down the bottom of the ionosphere and the neutral atmosphere, and the Saturn's magnetic field is almost exactly aligned with the spin axis. So to some extent, it's not overly interesting, but it does have a slight tilt because of the magnetic axis and spin axis are tilted relative to the solar wind, and so there's a plasma sheet that flops up and down. But anyway, you can see the neutral atmosphere over there and the pressures in millibars to give you an idea. All of these models, every last one of them, is provided by JPL. If you want, you can contact me and I'll give you the website. It's free. You can go online and you can get models of the ionosphere and the atmosphere anytime you want. You just need to put your orbit in and you can find out what's going on. But that includes the radiation belts. So radiation belts, atmospheres, ionospheres are all available directly from JPL online. This is the Saturn's polar cap. From the atmosphere is really weird up there. You can see it has a polar cap, and it's a permanent vortex at the Saturnian pole, and totally a surprise. And if you notice in the background there, it's about 2/3 of the way from the middle out. You can see it's hexagonally shaped. We see almost the same thing on Jupiter, only it's much more complex. It's got big, intense cyclonic activity in the polar caps. Both poles are really beautiful if you haven't seen the pictures. Anyway, the other thing is Titan, of course. These are the oceans, shows the oceans of methane and ethane. And this is the crude guess at the atmosphere with the composition and things that have been detected to give you an idea. And again, we have the pressure and temperature and things of that nature online for you. This is Uranus. Uranus has also, like Saturn, Jupiter does too, by the way, have rings where the moons have broken up, and you can see pictures here. The weird thing about Uranus, as shown in this picture, is that its spin axis is tilted almost 90 degrees to the ecliptic plane. It's like something hit it and knocked it over. And the magnetic field is at like 60 degrees from that. And so you get a really weird magnetic field at the Uranus. This shows you the my model of the Uranian magnetic radiation belts. Again, 1 MeV for the electrons, 5 MeV for the protons. Down below, you can see the ionosphere and the atmosphere. You get an idea of what it is, C2H9, and all these different chemical processes. I think, anyway, you can see the total electron content there, and that's mainly H plus, related to H plus. And on the right, you can see the temperature of the different components. Neptune, similar. This is Neptune. This shows the atmosphere. A guess at the atmosphere. I want you to know. We really don't know. We need to go back and remeasure it. The same for Uranus, but at least we have measurements, or at least a guess. And that's shown here. Then Pluto, we don't really know. They guessed. Here are your best guesses, and those again are in the JPL model, if you're interested. And the magnetic field, everything is there. So anyway, that's the ionosphere, the temperature profile, and the atmosphere. You can see that it's N2 mainly. And you can see that the ionosphere, you can see that it does have supposedly might have a Chapman layer. And on the right, you get the Pluto temperature. Now this compares the magnetic fields of the outer of all the planets, and you can see if Venus, the circle in there is the Venus surface, then the Mars surface, then really little bitty bitty down there is Earth, Saturn, Uranus, and Neptune, and Jupiter. Jupiter's a dot. That's why it's not really, you can't even see it, because the Jupiter magnetic field is 30 times bigger than all the others. Scaled is 30 times bigger, and it's just non-existent on here, the radius of Jupiter, since it goes out about 40 or 50 Jovian radiuses in the front direction. But you can see Saturn, Earth, Jupiter, Venus, Mars, Uranus, Neptune, how they all, they're scaled to be at 1 for the standoff distance relative to the surface of the planet. And on the right is the comparison of the ionospheres and the ionospheric density. And we have similar things for the atmosphere. And you can see the Venus, you can see where it folds off. Notice that the blue curve for Venus down there, where it folds off at 400 kilometers, like I was talking about. And so you can get some idea. Mars is the same way, it folds off below that. And then you can see the Earth is a lot more denser at 1,000 kilometers than the other two. And you can see the other comparisons of the ionospheres. Finally, let's look at just briefly at comets. I've had to do the atmospheric models for comets and the ionospheres. And we actually have measurements now, because if you remember, the Europeans went in orbit around a comet. And this is Halley. Oh no, I guess it's Borelli's comet. Here's on the left is a model of Halley's comet, of the magnetic field and such as we measured it when we flew by it. You can see my recent picture a few weeks ago of the Shinishan, I guess, Atlas comet. And I took that from my backyard about 2 weeks ago. And then you can see the neutral atmospheres and ionospheres for Halley's comet on the right over there. And we came fairly close, and so we were able to get some measurements and give you an idea of what the components and everything look like. But again, it interacts with the solar wind and varies with time as the outgassing rate changes for the comet. Now, we're going to change topics. I've sort of given you an overview of the atmospheres and ionospheres, and I would like you to remember that that they are presented online. You can get to all of them if you need to. We're now going to look at atmospheric effects, and we're right at 2 hours, a little over 2 hours. I'd like to take a 10-minute break. Ken, can we take a 10-minute break? Ken? Okay, let's come back at 2
Yes.
20.
Yes.
2:20.
Yeah, very good.
Okay.
Excellent. So we have a short break, so we'll be back at 2:20 in about 9 minutes. Yeah, the part two, the session just gets started.
All right. I'm gonna let me know if my voice changes, because I'm gonna have to stand up. Sitting for an hour and a half just about kills me.
Okay.
We're now going to look at what the effects of the atmosphere and the ionosphere on space vehicles are. We're going to start with atmospheric effects. Some simple things like drag is obvious. Oxygen erosion is not so obvious and is a serious effect. It, be blunt, it's completely destroyed surfaces on a number of satellites below 500 kilometers, just dissolved anything that was plastic has disappeared on the front side, and the back side is can be black with tar from all the contaminants and stuff coming out of the spacecraft, whereas the front surface will be pure and sterile, clean, with no plastics. Thermal blankets that have or surfaces that have gold on them, as the particles will, the oxygen particles will penetrate and eat away the plastic behind the gold, and all you'll have is gold foil left after about 2 or 3 years in orbit. The surfaces on Hubble were scoured in the forward direction. In the back directions, there was mud and stuff like that. Whole satellites are like that. And it's so anyway, oxygen erosion is very bad and causes a lot more damage than people realize. And then we'll look at glow. Glow is probably the least understood process. I think I still have the only review paper on the field on the subject. And glow, I was told by Owen, Gary, and I were talking about it, and Owen told me that he could read by the glow on the Skylab. It was so bright on one side that he could actually read his initials and things like that, his stuff that he had when he was doing extravehicular activities. He could actually read by it. So it's significant. Anyway, let's look first at drag. Drag is fairly simple. The force of drag is equal to 1/2 the density of the atmosphere, v squared, of the relative velocity, the two between the spacecraft and the atmosphere, coefficient, drag coefficient, and then the area that's exposed in the forward direction. My early career, I got to take part in a number of Air Force exercises where we tried to see how low we could actually fly a satellite. The lowest of the satellite that I'm aware of has ever flown is Air Force Cambridge Research Labs shot a uranium ball around the planet, and it went around in about a little less than 80 minutes at 90 kilometers and made one orbit before it came in. And that's the lowest that I'm aware of. Anyway, they called it, trying to remember the story. Anyway, it was this shot heard round the world, and heard was H-E-R-D. They always thought that was real funny, but anyway, shot heard round the world. So the drag coefficient typically for space vehicles varies between 2.2 and 4. The problem is that's a large factor there. And most objects are very complex. And the single most difficult thing to determine is the drag coefficient and what's called the accommodation coefficient. The atmosphere, the way that particles bounce off the surface is very critical to determining the drag coefficient. So 2.2 to 4, and it can be anywhere in there. And depending on whether you got a flat plate or a narrow wire going in the direction, you get a huge range of drag coefficients. And for example, the area of the space shuttle was about 50 meters squared, whereas the base, if you flew it broadside, the wing sides towards the towards direction you were going, was 400 meters squared. The velocity of the space shuttle is about 7.6 kilometers per second at 400 or 500 kilometers, and the density was about 10 to the minus 15th grams per cubic centimeter. And so if you calculate that out, it comes out that the drag force is about 300 to 5,000 dynes. That's a huge difference. And depending on whether you fly it in the streamline going rocket mode, if you want to think of it, versus flying the base straight into the atmosphere. And drag was a significant issue for many of the satellites and such that I worked on for the atmosphere, for the Air Force. Basically, if you remember, we used to fly satellites very low to take pictures of things, and in low altitude, of course. One of the things that you have to do is you have to increase the mass of the spacecraft. In fact, if you wanted to keep something up there, the best thing to do was to put a chunk of uranium or something like that in the satellite, because you didn't have to go very far to launch them, only a few hundred kilometers up, but you wanted to have the mass so that the drag coefficient would go way down. That was the main thing, is to try to have the area to mass ratio very small. Anyway, so to give you some idea. Now this is a nice plot. This is for about a 1 square meter surface, basically a standard Explorer class series spacecraft, as a function of altitude, and with the F10.7 index. The F10.7 index is the iron line, radio wave line from the sun, and is used as a proxy for solar activity. Has been used for many, many years as a proxy. It just works. I'm not going to explain why. They use F10.7 as a proxy for geomagnetic activity on the sun. It's integrated over the area of the sun, and they can get it very easily by listening at that at 10.7 centimeters, and just plotting the intensity of solar activity at that frequency, and that gives them something that has been discovered by trial and error to be a good representation of the drag coefficient effects of the drag on the spacecraft. And you can see here that if you're at 400 kilometers, you be up about 4 or 5 years if it's really quiet. In other words, the sun's down around 75. If it's up like it is right now around 250, you can decay in less than a year at 400 kilometers. 500 kilometers, you can see again that you can go for decades, 30, 40 decades at 70 for solar quiet. Whereas if you go to 250, you can decay in less than a year or two. And that's what's happened. Spacecraft literally fell out of the sky when we have major geomagnetic storms because of the density, if they're below about 400 or 500 kilometers, as did happen to the one of the recent launches of the SpaceX satellites. Now, this is a very interesting plot. This is from about when was it? 1989 was a major geomagnetic storm in March of that year. And what you see here is the solid line is the geomagnetic index, and it went up to 1400, the particular index that they were plotting. On the right over there, it's 150. It's the AP index to be precise. On the right over there, that's the index. The histogram plots are satellites that were lost. Now, what do we mean by lost? It turns out that Cheyenne Mountain, for the Air Force Cheyenne Mountain facility, monitors the satellite constellation, and there are always a few satellites, a few hundred, that they can't, they lose them for various reasons. And bottom line is it's usually about 200 at a given time when this measurement was made. And then all of a sudden we had the geomagnetic storm when the index went up above 150, and that shot the atmospheric density way up. And as you can see, they immediately started to lose track of satellites. And so within a very short time, a factor of 6 to 7 more satellites were lost. That went from 200 to 1400 satellites. They lost their tracks because of the drag on the satellites. They basically fell out of the sky. They would drop tens of kilometers to hundreds of kilometers in some cases and decay back into the ground. So that's what happened, and you can see that it took them something like 10 to 15 days to recover all the satellites that were lost because of the atmospheric drag calculations. Now, if you wanted to launch a war during that time period, which is what they worry about, if you want to launch a war during that period, they wouldn't know whether your satellite, where your satellite was. And people are talking again, I think the Chinese and Russians in particular are starting to talk about orbiting atomic weapons in space. I've seen some articles on that very recently, that they're threatening to start flying them again. And you want to track those, obviously, and but if you can't track, if you lose track of them, what in the world? They could launch an attack, and that's what one of the main concerns is about all these kinds of things. Plus, all the fact that the satellites run into each other, the space debris problem is accentuated by these kinds of effects. Now, let's look at what I consider a major issue. You'll see on the right up there, that was black coated Galileo blanket material, thermal blanket material. Turns out that black paint is very susceptible to atomic oxygen erosion. You can see the gold showing through, where after 4 or 5 days on the space shuttle, they flew samples on the space shuttle, the black paint was eaten away within a few days of going in the ram direction on the shuttle. One of the things they did was they made sure that when they launched Galileo from the shuttle, that it was going base first, so that they shadowed the satellite itself as much as possible from the atomic oxygen erosion rather than replace the surfaces. So this is why we grew concerned about possible atomic oxygen at Europa, is because of the thermal blankets can be eaten away. The paint, which is JPL has passive thermal control on all its satellites, and as a result of that, we have to design them to survive thermally stable modes. And if you're having your thermal blankets eaten away, um, change their alpha over epsilon, you get really worried about it. You can see down below that, there's some other samples that they flew on the STS-3 thermal blankets. And on the left is prior to launch, and nice and smooth and stuff. On the right is a typical surface after being exposed in the ram direction to the atomic oxygen race. Basically what happens is atomic oxygen erodes all kinds of organic and paint samples and such and plastics on on low altitude satellites, and it can be really serious problem. They've brought satellites back when they've recovered them, and they found anything that was plastic in the ram direction is gone. It's amazing how fast they can eat things away, and so you really need to do this. And that's what I was saying. The Japanese silver is one of the things that's really bad. Turns out that silver, when you expose it to oxygen, even on the ground, as you know, it forms a flake. The silver oxidizes, and you can flake it off. And that's why silver has a real problem being exposed to any kind of oxygen environment. And in space, when you have thermal cycling, the silver actually chips off because of its forms flakes, and then the flakes get stressed and they fall off. This is another example of that. This is actual calculations for Teflon and for Kapton. Teflon, it turns out, is about 10 times tougher than Kapton to erosion. The only problem with Teflon is that it's about 10 times more sensitive to radiation. You can't win. It's great for atomic oxygen erosion, and it's crappy for radiation effects. It turns white and oxidizes and all sorts of garbage when the radiation hits it. But here's what's plotted here. There's sunspot maximum. That's the solid line on the right. You can see that down goes up to about 10 to the 0 or 1 or 10, yeah, 1. And then you've got standard atmosphere. That's what we assume for most missions. That's the dashed line. Then your dashed dot line is for solar minimum. And there's a huge difference in the mass loss per year from Teflon versus Kapton. You can see the top scale is for Kapton. The bottom scale is for Teflon. And that's the mass loss versus the atomic fluence, atoms per square centimeter per year. And you can literally, surfaces just disappear. And you can think of what's going on right now. It'd be interesting to see what's happening to this SpaceX satellites, what they have exposed, and if they ever recover any of them, to see what surfaces are disappeared. So this is an important consideration. In fact, this is a critical consideration for how long you want your satellite to last. And it's a real problem in low Earth orbit. And we were fearful that it would be a real problem at Jupiter because of the atomic oxygen ring around in the orbit of Europa. So here's some of the things that erode and how badly they erode. 10 to the minus 24 is sort of a canonical number, and you can see the reaction efficiencies. Teflon is okay. You can come down to epoxies and polystyrene. Kapton, you can see the different kinds of Kapton and Tedlar and stuff have real problems with the problem with stuff. And Huntsville and Marshall, you can see, has done a lot of measurements of this. And Johnson and Marshall, Johnson because of the space station, and Marshall because of just general materials interest that they're a lead in. And you can see, like, for example, Mylar and polyethylene in particular is very sensitive. But then you get to things like metals and aluminum or magnesium, and no effects at all. Yet silver is basically disappears in orbit. And so you have to be very careful about what you put on the outside, because a lot of people like to use silver in particular for electrical leads. And anyway, give you an idea of some of the particles environments. I have lists of these that I've saved over the years if anybody's interested. Now, here's a unique effect. They call it shuttle glow, but it's for all satellites. And basically, as we'll see what happened. By the way, I want you to notice the particles right over the OMS pod there. They're little pairs of particles. That's garbage coming off the shuttle. That's chunks of ice coming off the shuttle. The pairs of particles and stuff is actually one particle, and it's moved between pictures. And what what you're doing is you're looking at the tail of the space shuttle. You're looking at the thing the V thing down there glowing is an electron emitter, if I remember. And then the glow is the stuff off the OMS pod and off the tail piece. That glow that you see is not a reflection. That's an actual interaction with the atomic oxygen in the direction the spacecraft is moving, as we'll see. It's moving in to the right and up. And that's why you see that the tail is lit up and why the OMS pod is lit up. If I can get it to work, I'll show you a movie of that an astronaut did. It's probably the only movie anybody's bothered to take of it. And so you're seeing some unique data here, I believe. I haven't heard of anybody actually bothering to look at it but I think they should. Depends on what kind of sensors you're flying. Because if you're sensitive to basically orange light, you got a problem. Now, the color's a little off here. It's more orange, but you can see the whole back end of down on the right, you can see the whole back end of the shuttle lit up because they're moving moving upwards, directly upwards against the atomic oxygen. So astronauts have photographed and talked about surface glow for many years. Like I said, I actually had a discussion with Owen Garrett about it, and it greatly enhances glow observed following thruster firings. And it basically directly related to the cloud of gunk around the shuttle or Mir or any of the other space stations and such that have been up there. And the ISS has the problem, of course. Surface glow exhibits basically, as it says here, a continuum. And I'll show you the spectrum of that as best we can determine it. And the problem is that they take pictures through the shuttle windows, the main, and those seriously attenuate the actual flux. This gives you some idea of what the relationship is. This top thing would be a really bright aurora, and that's at 100,000 Rayleigh per angstrom. How much photons per angstrom you get. And you can see day glow is down there. Day glow is what you can, as I was saying, atomic oxygen at 6,300 angstroms. You can see your hand against the sky. And then you got weaker and weaker aurora there. Winter twilight air glow. You can see night glow, all the different kinds of air glows and day glows and aurora. And then you get down to around 100, you get what the AE and STS glow values were from the actual glow, observing it. And you can see those. Look, they're all worse than full moonlight. And you know, full moonlight is pretty bright, and it messes up a lot of telescope observations. And You can even see large space telescope like the Hubble's, what they're referring to there. And you can see where it is. And then zodiacal lights. I've saw zodiacal lights in Roswell a couple of times. It has to be really dark, but you can see them, and that's the glow from the meteoroid material falling into the sun in the equatorial plane of the ecliptic plane of the sun. So let's see if we can, let me see where I want to go. Okay, I'll go one more. This is a plot of the brightness at 7,320 angstroms in terms of Rayleighs as a function of altitude as measured by various shuttle missions. And you can see the N2 density and the O density. Now, people begin to think that it's primarily, as we'll show in the chemical reactions, mainly due to the atomic oxygen, but it's also affected by the N2, because it's N2O is apparently the atom that's emitting. And so it's both a function of nitrogen and oxygen. And you can see that the measurements, that's the dots over there on the left, tend to follow the atomic oxygen above 180 kilometers. So now this is what you're going to see a portion of is notice that the arrows there point the direction from which the atomic oxygen is coming. And you can see that it's coming straight down, and so the Ohm's pot is glowing. You go to 30 degrees and it starts to move. You go to 50 degrees and it disappears because it's coming from underneath, and 97 degrees, and then it starts to come back up again as you rotate to the side in 150 degrees. Now let's see if I can get this to work. I may lose everything. So let's see, what do we in show? And let me see, okay, let me see if I can do this. Stop share. And then I'm going to share. And let's see if it will work. And it looks like it's going to.
Oh, now it's all white. We don't
Oh,
see it.
you're not seeing it?
Not seeing it, but the initial page with the
Oh, I got you. I got just a second. Stop sharing. Let me see if I can get it to work. I may not be able to get it to work, but I thought I had it figured out. Let me see. Oh, come on. Share. Let me see. I'll try it one more time, and if it doesn't work, we'll give up. All right.
Yeah. Oh, yeah.
Can you see it?
Yes.
Okay, that's the electron emitter. Now watch to the right there. They did a nitrogen dump. The Ohm's pod uses nitrogen for steering things, nitrogen gas. Notice how bright it is after they fired the nitrogen plume. They use nitrogen to control attitude on the shuttle. Now it's going to explode tremendously here in just a second, and watch how long it takes for it to die off. This is a handheld camera by one of the astronauts, why it's jumping around and everything. And it's probably one of the few picture movies we have of this stuff. But wait for it. Come on. There we go. Somewhat bright. You have to admit, that was pretty dang bright. And look how long it's taken. It's taking minutes to go away. So anyway, let's see if I can get rid of this. And let's see, stop sharing. And let's see if I can share again. And let's see if I can do this. And then let's see if I can do this. Are we back?
Yes.
Okay. So now you get the idea. Literally, as Owen said, you can read by this stuff. And now here's some other things. If you look on the left over here, you'll see the Canadian arm on the I don't know if you can see the marker or not, but I don't know if you can see my arrow, but right there's the Canadian arm on the right, sticking up parallel to the shuttle bay. If you come over here, you can see the Canadian arm again, and then this is the same thing. They took a spectrogram of it, and basically what they did is this is a plot of the light output for each one of those different materials. You read them across the bottom there: magnesium fluorides, zinc 306, Zot 302, poly, whatever it is, 401, carbon cloth, chemical film, and aluminum oxide. And you can see that each one of the different types of materials has a different characteristic emission profile from the shuttle glow. What they now believe that is, they explained to me, was that each of the different materials is at a different temperature. And so the temperature determines the chemical reactions that are going on, and therefore controls the amount of glow that you see above the materials. So it's also dependent on the surface material that you have on the shuttle. Now, this is what the continuum looks like, and it's pretty much screwed up because they took it through the window, but the laboratory NO2 continuum, we measured that at Cambridge Geophysics Laboratory, Cambridge Research Labs, whatever you want to call it. And that's the top curve. That's what NO2 continuum looks like. And then the window, of course, screws things up. And so the STS41D spectra are filtered by the window. But we believe that it's NO2 continuum glow. They think that's what nitrogen dioxide. They think that's what's glowing. And this is the possible explanation for this. Fortunately, at JPL, I worked with a bunch of atmospheric chemistry people, and they were able to simulate this in the laboratory also. And what we think happens is you got CO2, H2, H2O, CO2, and crap stuck on the surface. And in the contaminant cloud of NO2, N2O, and things like N2, helium, all sorts of garbage from the shuttle. And then you have oxygen and N2 coming in at 8 kilometers per second. And obviously that's at those velocities it can become ionized. So you have on the right, you can see what we think is happening. Nitrogen, ionized nitrogen comes in, or N1, I guess that's neutral nitrogen, neutral oxygen comes in, and they get combined chemically, and then they come off, and NO glows in the gas state. Then you have NO being hit with another oxygen atom, and you get NO2, and that radiates. It's all these gases combine and get excited, and then they think the primary process is NO2 going from an excited state to the 2B1 state down to a ground state, and radiates this orange glow. So that's what I've been talking about. And I think you have to admit that was pretty spectacular, that movie. I mean, this is the guy looking out the back end of the dumb shuttle. It's glowing hellaciously. Anyway, what can you do to mitigate it? Well, you get the heck out of the low altitude regime, get up above 800 kilometers, it turns out. You can vary your look angle so you're not looking into the ram, which is where almost all the glow is. You can limit thruster firings during observations, so you don't fire the thrusters, the nitrogen thrusters, and screw yourself up. You can use filters, of course, to filter it out. You can change the materials. As you notice, several of the materials are almost an order of magnitude lower glowing, or you can control the surface temperature, which was the other suggestion. So anyway, glow. We covered drag and we covered glow and oxygen erosion. So let's now look at ionospheric interactions. We've looked at the neutral gas interactions. Let's look at them. Here's what's going on. Look at the right on that little movie. Can you see the movie?
Yes, yes.
Okay, you're going up, and normally you would do 1, 2, 3, 4 to a satellite. Then if you come up and there's a ionospheric disturbance or something, a geomagnetic storm or things like that, you get these regions of enhanced density, and it screws up the signal. So you get 2, 3, 1, 4. And so the bottom line is this: the ionosphere affects signal propagation, as we well know. And if you were to map the regions of ionospheric turbulence, if you look down at the bottom down here, you can see at noon, it's relatively minimal. If you go to the polar caps, you can see there's all kinds of, well, it's typically around 10 dB to 15 dB in interference over the two polar caps. But notice at midnight what happens. There's this thing called the fountain effect. And basically what happens is there's the reason you get a dichotomy there is because the magnetic field comes down near midnight, and the ionosphere gets upset at the base of the magnetic field lines and comes up, and you get the spread for the north magnetic field and the south magnetic field, and you get it's all magnetically field controlled over the polar caps and this fountain effect near local midnight down there. And then you can see at solar minimum, it's just sort of blurred out. But at solar maximum, if you notice the split, that's a well-known effect called the fountain effect, if I remember exactly. And it's one of the things that people use to try to communicate. You can bounce off those layers at night. And if you remember our ionospheric patterns, they change dramatically between day and night. And you get this much higher, you get high changeable densities between the two regions. And then you can get these storm-induced regions at local midnight, near local midnight. And we actually saw that on some of our satellites. We had to pull up the ionospheric models, and we compared that with the noise that one of our, forget which satellite it was, but I have a paper on it, that we measured the, used the model on the left over there and actually picked up that region of turbulence that was screwing up the data reception from one of our satellites at JPL. It was one-to-one correlation. It was beautiful. So that's what you see on the left actually happens. I want to guarantee you that you get these regions where you get a lot of noise. Okay, let's look at another plasma interaction. This one on the right, lower right, is something, a test that we ran at JPL I took part in, is they took some astronaut uniform material. I have some samples if anybody wants to come by and look at them. And it's the orthocloth and stuff. And what you're seeing there where it says flashover discharges, that's where the thread was. And it was the threads were apparently non-conducting in some way, and they glowed where it was sewed together, where the cloth was sewed, and when we exposed it to an electron beam. So what we did was he took cloth and all the other suit materials, put them in an electron beam, and some of them glowed, some of them didn't, from arc discharges. Basically, the suit material is non-conductive, and it would discharge. And so plasma, on the right, upper right, what you're seeing is a plot by NASCAP charging code of the wake behind the space shuttle when it's flying in the bottom forward position, the maximum drag position. The plasma is coming from the left, and you get this wake that's created back there. Now, why is this important? As we'll see in just a second, the aurora come down in specific regions, and they, by the way, they do intersect with the space station. The space station flies through the auroral zone sometimes, particularly when these really bad storms occurred the last few weeks. If you remember, we've had some storms with the aurora down over almost over Houston. And anyway, to make a long story short, you have a major depletion of the low density plasma behind a large space structure, in particular behind the shuttle or behind, and I'll show you small satellites, the same thing happens. Even behind wires on the satellite, the antenna wires, you'll get a wake structure created. And the auroral are such energetic particles, tens of keV as opposed to 1 eV for the, or less for the ionosphere, that you can get spacecraft charging in the wake region. This shows you a simple it was a 1 meter satellite as it went up and down in orbit, Explorer 31. As it went up and down in altitude, it would go in and out of the ionosphere. The top one was at 500 kilometers. By the time you get to the bottom is at 1,200 kilometers. And what you're seeing is the satellite had a Langmuir probe, if I remember what it was, and it would measure the electron density. And so you can see that when it was faced into the wake, that's at 180 degrees, 0 degrees is into the RAM. You get high, we normalized everything to 1. This plot normalizes everything to 1 in the direction you're going. And you can see there's a huge 2 orders of magnitude depletion at 500 kilometers in the electron density as measured by a Langmuir probe. As you go to higher altitudes, that goes away. And what's happening is that you're going from a hydrogen poor region, and mainly oxygen dominated regions. So you got slow, big ions versus H plus, which is a small, lightweight, nimble proton, can't get into the wake because there's not much of it. Whereas you get to higher altitudes, it becomes dominated by hydrogen. You see it's almost 95% down there in the lower picture, protons. And as a result, the wake disappears because the hydrogen has enough energy to get into the wake, and there's enough of it to get into the wake and cut things down. The oxygen is basically denied entry into the wake. And as a result of that, the wake becomes very dense, becomes very deep, 2 orders of magnitude compared to less than 1 order of magnitude as you value in height. So bottom line is that you can get a massive depletion, 2 orders of magnitude at 500 kilometers in the ions getting into a plasma wake. And as a result of that, the electrons have a hard time getting in too at 1 eV or less. So everywhere there's aurora. There's aurora at Jupiter, there's aurora at shuttle altitudes, there's aurora at the space station altitudes, and this is what they look like. And I spent a summer in the Arctic studying the aurora, flying balloons into them. It was a lot of fun when I was an undergraduate. And so I learned a lot about the aurora. This is some calculations that myself, Joe Wang and Phil Leung and Jerry Murphy did back in '94. We modeled the effects of a large solar array panel, such as would be for the space station, to see what would happen. A is just the ambient plasma, ionospheric plasma at 500 kilometers roughly. And you can see that the model, the dots are the electron density, that the electrons, the EV or less electrons are pretty much kept away behind. The plasma is coming from the left, obviously, and you're flying a big flat plate into it, and you can see there's a big gap. There's no electrons in the wake. As such, the potential contours become fairly pronounced. But then what happens is we start to do multi-body charging. We stick a astronaut or stick another satellite or a boom or something in the wake, and you can see it starts to get a little charging, and because some of the electrons can get to it. But then you get a real problem. You get the auroral charging, and that's on the bottom, the C plot. You can see the electrons, the high energy electrons, we're talking about 10 to 20 keV electrons, can get into the wake, and they can charge an astronaut, charge the charge up a body there, and then ultimately you can also bias the body in the wake relative to the plate, and you get all kinds of weird stuff going on, as you can see on the D panel. That's where there's aurora and it's biased to see what you can do. People actually did that. They took a big plate, and AFRL, AFGL took a big plate, flew it, and biased the body in the back. Actually, it was a Langmuir probe sticking back there, and they biased it plus and minus, and they demonstrated all that you see here. Now, this is the probability of running into an aurora as a function of magnetic local time versus the corrected geomagnetic latitude. Corrected geomagnetic latitude means we're in geomagnetic coordinates as opposed to geographic coordinates. The pole is offset about 11.5 degrees from true north in Hudson's Bay, and the net result is that there's offset spin effect, and you also get the South Atlantic anomaly and other weird things because the magnetic field is warped, and it's not just a simple dipole that lines up with the axes. And you can see that it's about 0.0025% of the, that's the fraction of the time. So it's less than 0.25% of the time you'll run into an aurora between about midnight, right before midnight, and 75 degrees north magnetic latitude, not geographic, but magnetic latitude. And as I say, is offset towards Hudson's Bay. And so you can see that there's a finite region in there where you get significant charging. And these are the unusually bright aurora. We're talking about 5 to 10 keV, maybe 20 keV beams of electrons. In fact, this shows you the same thing. This is from DMSP satellite. And basically what it did was, it's in a polar orbit. And you can see on the right, the aurora, that's a picture of the aurora that's flying through. Basically what it does is it spins and has a little photomultiplier tube. And as it spins, it records the signal and sends that back to Earth. And you can see the raster pattern up on the upper left there, and sends that back to Earth. And they reconstruct photographs of the cloud cover. It's mainly for cloud cover, but it turned out that it also recorded the aurora quite well. I've got hundreds of spools of this stuff. This is beautiful to look at, the aurora from space, from DMSP. Anyway, what you see in the upper left is the current from the aurora at 5 and 10 keV. And you can, on the right over here, you're seeing the track of the satellite. And as it passed through the main portion of the auroral arc down there, the yellow part, that maps exactly to the satellite potentials. And so it was between 100 and almost a kilovolt of potential on the satellite as it went through these the auroral region down there. So the left is the measurements as you went through the aurora on the right. So hopefully that's clear to you. And this is a beautiful picture. It really illustrates what we're talking about. And the space station passes towards the bottom of that. Now, how does the space station handle it? Well, we'll see in just a second. This is the problem. Again, this is the same picture, electron beam off up at the top, and then we turned it on and the threads lit up, and you can see the stitches down there. That's where what was lighting up. And this is the test beam. It turns out that if you get a potential difference of 150 volts across your body, you're dead. That's right, 150 volts arc can kill you. And now, how do they know this? They stuck a bunch of sheep inside an astronaut's outfit and arced the hell out of it. That's how they tested for it. Poor sheep. Anyway, I'm not sure we arc the same way, but they didn't do it on an astronaut, so I guess that's probably good. But as electron beam at 15 keV and 5 nanoamps per square centimeter, which is about what it is in an aurora, and you can see the arc discharge of the ortho fabric. That's the white stuff, and stitches glowed and things of that nature. So bottom line, you can kill an astronaut, okay? At least the people that flew the space station believed they could prove that you could kill an astronaut. Marshall took the lead role in all of this, and I took part in the evaluation of the ISS protection system, and I'll go into that in just a second. This is all the different things that don't conduct or conduct. The metal foil, there are metal foil decals on the astronaut. There's aluminum bands and stuff. And in fact, they put duct tape around their wrists to make sure that there's no leak. And then they got gloss white paint, silver eyes, Teflon on glass, epoxy, and all kinds of stuff. And then these are the NASCAP runs showing you what happens. Again, the wake is coming from the left over there on the shuttle. And you can see an astronaut in the bay, and you can see that it got up to 2,500 volts on the astronaut around his face plate. That's on the right over there. So we were able to show both by measurements and theoretically that an astronaut can light up an arc in an aurora. Not good for the astronaut. And what's worse is that unlike the Russians, the US has electrodes on the heart that pass outside the spacesuit into a box that apparently transmits the heart rate of the astronaut. So there's 2 wires that run in, go across your chest, and pop back out the other side. Good reason not to measure your heart rate. But anyway, that's the way they do it. And now, let me show you some of the results. This is actual results from a European Eureka solar array that they brought back that failed. So the bottom line is, what did they do on the ISS? They flood the thing with plasma in the wake. They have plasma emitters that are required to be turned on when the astronaut is outside. I was on a team that evaluated the Boeing procedures. They wanted to do away with the plasma flooding because it's a pain in the butt to have to turn on the plasma emitters so far ahead, have the astronaut out there, and then turn them off when he goes back in. And we were able to show beyond a shadow of a doubt that the astronaut might get killed if you pass through an aurora at the same time the astronaut is in the wake of the space station. And we argued with them, and they told us that they never had any problems with the spacesuits and that they didn't think there was an issue. 3 weeks later to the day, one of the astronauts had a broken water line and almost drowned in the spacesuit. And this is after they assured us that they never had any problems with the spacesuits. Needless to say, we won our case, and they still use plasma emitters to flood the wake of the space station to keep the astronauts from charging up in aurora. And I think that was well worth the effort. Anyway, this big solar arrays on the space station. And what you typically have is you have a solar cell cover slide. That's a little piece of glass. and then you have the solar array immediately below that, and then that's mounted on a fiberglass substrate with grounded metal edges, as you can see. Now, what did we do? Well, we took and put these things in the chamber, and we shot electron beams at them. And we found that as the potential went up, and you scanned across the surface, as long as you were over plus or minus 100 volts, you would exactly what you would see. You would see the little uncovered wires. See the little wires there, right under the word slide, that connects the solar arrays. And because they're not grouted, they expose the potential to the space environment. Now, why is this important? Because people want to crank the voltage on the solar arrays well above 100. They want to go to 1,000 volts, things like that. They want really high voltage solar arrays. And anyway, you can see on the left, that's what happens when you bias it positive. It sucks in electrons, okay? On the right, you're biasing it negative, and you're sucking in protons, ions, O plus, whatever. And you can see that the potential drops right at where the wire is exposed. All this is well and good. Then magic happens. And I mean magic happens. You crank this sucker above about 200 volts, the potential on the solar array, and all of a sudden you get something called snap over if it's positively biased. And it turns out that because there's so much, electrons are about 40 times faster than protons and ions, you find that about 39/40ths of a solar array will float negative, and the other part floats positive. I'm sorry, the opposite. The negative portion of the solar array is 39/40ths, and the positive part of the solar array is 1/40th of the total area, because it attracts electrons so easily. Electrons are basically 40 times faster getting in, and so positive part of the solar array is grounded almost immediately by the electrons, whereas you need to suck in a lot more ions, and so it's 39/40ths of the area floats negative to suck them in. Anyway, magically, and I'll explain why in a second, you go hit 200 volts and the whole surface becomes a plasma cloud. And what's happening is that the electrons coming in, they're sucked in to the positive region, little wires. They emit secondary electrons prodigiously above at 200 volts and higher. You're knocking off 2 or 3 electrons for every one that comes in. And you create a cloud of negative electrons over the surface of the solar array wherever there's an exposed wire. And this is not good. Anyway, then it's basically saps power, because what's happening is the electrons are you're soaking in, you're pulling electron current into the solar array, and all of a sudden the whole solar array, not just the little wires, are sucking in electrons, and so that whole surface begins to absorb electrons. Okay, and the power goes down for that part, that 1/40th of the array. The power can drop dramatically. That's not so bad. Because you still got 39/40ths over there on the other side. So what happens when you bias it negative? Well, somewhere around 150 to 200 volts, it starts arcing. And the reason is because you've got ions coming in, and you can create a little plasma, and it turns out that can lead to an arc discharges called a triple point. I'm not going to go into that in detail here, but what happens is that you create a little plasma cloud and the voltage drop between the solar cells is enough to generate an arc. And at those voltages, a negative 500, because you start the field emit electrons at above 200, 300 volts. They acts like an electron emitter, and you get a cloud of gas and plasma there, and it breaks down. I'll show you in the next view graph exactly how that happens. Anyway, the results of that is on the right. That's the discharge caused by this phenomenon called arcing on the left panel, and the results you can see destroys the solar array, just destroys it. And it turns out that lots of solar arrays, they series wire them, and so that you build up to large potentials from one side of the solar array to the other. What you have to do and ameliorate this circumstance is you have to alternate to make sure that there's never any more than about 100 volts between solar array panels. I have a movie that I showed in the past that goes into great detail on what happens when you bias the things that way. You have to have small inner solar array cell potentials less than a few hundred volts, or you're going to get this phenomenon. It depends strictly on how you wire it. And this is the part of the killer. It's called passion breakdown. Basically, if you get a neutral gas in between the gaps there, if the distance between the gap is enough and there's enough density, that's what the pressure times the spacing parameter down there is. You get an arc at those voltages that you see the voltages goes from 100 to 10,000. And these are all the different types of atmospheric gases that you have to worry about. There's air, nitrogen, CO2, capton, helium, hydrogen, all that kind of garbage. And the problem being that think of it this way, if you have two plates and you put a gas between them, as you crank up the voltage, you get to a point where you start to field emit electrons. The electrons travel into the gas, and if they're going fast enough, they'll ionize the gas. And if they ionize enough of the gas, you're going to generate basically lightning between the two plates. Now, if you increase the pressure enough, the electrons aren't going to go very far because there's lots of neutral gas and it stops them. So you have two extremes. You have, if you pump it down where there's not much gas there, you can't get an arc discharge started. But as you crank up the pressure, you go through the passion breakdown value, where the pressure times the spacing is just right, and the gas will break down, and the arc will propagate through the gas to the other plate. That's when you get the arc discharge. If you go increase the pressure, like in the lower atmosphere, then you're fine. The atmosphere insulates you. We flew the Spear satellites. I worked on a Spear mission, worked on that where we'd crank the voltage up till we went through the passion breakdown to check and see how all this does, because our customer, this was when I was in the Star Wars program, wanted to know how high a voltage they could generate. And if you do it right, and you put the insulators and things, that's why they have the funny glass insulators on high voltage lines. You'll see about 5 or 6 rings of glass insulators on all the huge power lines. That's because they break down the passion breakdown between each one of the surfaces. If you had just one, it wouldn't do enough. So you put lots of little glass rings to break it down. I think you can remember, I think you know what I'm talking about. Anyway, we had this happen on SCAFA, a satellite that I got all my awards for. Spacecraft charging at high altitudes, P78-2. We launched that into semi-geosynchronous orbit, and immediately the traveling wave tube failed. What had happened was that there was enough gas in there and enough the spacing was just right that we kept getting passion breakdown between the two plates of the traveling wave tube. Well, somebody said, just wait. What'll happen is that the arcing will burn off the surface to the point where you lose the resonance. And sure enough, it did after about a month. Can you imagine turning on your traveling wave tube to transmit your data and it arcs like hell? And then all of a sudden it goes away and it heals itself. Anyway, that's what happened on SCAFA. All right, let's go to the final area, contamination. I was going to show you a picture of the shuttle flushing the commode, but Ken told me not to. They flushed the commode on the shuttle and it puts out a 5 kilometer long, well, frankly, a cloud of ice formed from the urine. And that ice, by the way, comes back and they have urine ice pits on several shuttle tiles that were from people flushing the commode and then flying back through their cloud at about 3 or 4 kilometers per second. They don't do that anymore, I think, on the space station. You don't flush it overboard. Anyway, the bottom line is that the shuttle puts out all kinds of garbage. Upper picture on the right is the mirror, and it's showing all the garbage floating around it. On the left, you see these lines of particles, starts right over on the left on the OMS pod and goes up to the right. That's one particle. That's ice chunks floating off of the OMS pod. And so there's big chunks of stuff floating up there. And then there's lots of gas and there's garbage like that. In fact, you found when we pulled back the LDEF, the long duration exposure facility, when we went to look at it, I actually, one of my colleagues got to look at it and he reported back to me. The front side of the LDEF was up there for 5 years and they had to pull it back because it got hit by a geomagnetic storm that caused it to drop 10 to 20 kilometers in a day. And as a net result of it, they were going, if they didn't recover it with a shuttle right away, they were going to lose it. So after 5 years, they had to bring it back down. But what they found was it flew in one orientation. And they found that the ram direction was perfectly clean. Everything that was plastic was eaten away. They had gold foil because the particles, atomic oxygen particles, penetrated the gold and ate away the plastic behind the gold. But when they looked at the back of the thing, the wake direction, it was coated with basically mud. I've got pictures of it. I guess I should have shown them. It was basically black with, looked like tar and garbage all over the backside of the spacecraft. And basically from all the outgassing from rubber decaying and things like that. And you remember you have wires and junk like that, and it outgasses. And I'll show you what the most common one is. And here, guess what this is? You know it. You know it this is a very familiar contaminant to you. This is new car smell, dioctyl phthalate. And it's basically the stuff that comes out of vinyl. And whenever you get in, when you buy your new car, this is exactly what you're smelling. And that's why you can't see out. You remember it coats for the first year or two, it coats the inside of the glass on your car and it gets really bad. Well, it's really, this shows you the absorptance thing. You can see that at 3,000, 1,800, I guess 1300, etc., you can see where the huge absorptions takes place. And this is the most common of the outgassing compounds that comes out. So you gotta be really careful of what you do. And I'll show you, this is the so-called LES 8 and 9 spacecraft. They were fired into orbit, and they were supposed to be stealth satellites. Unfortunately, as they were separating, as I understand it, they retrofired and coated the satellites in the flame from and gunk from the secondary engine, and the net result was they glowed like hell. And this is the net result, is that you could see the things, still satellites that you could see. It was somewhat of an embarrassment, but they did learn a lot. The QCM is a quartz crystal microbalance, and where they measured the garbage rate on the satellite. And you can see that when they did the retrofire, it just coated the whole thing and made it highly observable. And anyway, I thought you'd find this intriguing. This is just the garbage coming out from the thing. Now, here's a list. I have much more lists, and you can get these from Marshall or Johnson. I think Johnson does the same thing. I know Marshall does. And I think also Langley. This is a whole bunch of generic materials that really are messy. Epoxies never cure. If you fly an epoxy, you can bet that it's going to be cracking and giving out gas for the entire time of your mission. Anything with epoxy in it is just a disaster because it doesn't cure completely, and it cures over the lifetime of the mission. And when it cures, it cracks and the gas comes out. You got all these polyterephthalates. That's the gunk I was talking about, the new car smell kind of garbage. You got foams, which are epoxies. And anyway, you can see the bottom line is that just about anything plastic or epoxy is going to outgas. And then lubricants are really bad. And here's a whole bunch of them, all the different species that can come out. So bottom line is, if you paint it, you're stuck. If you use epoxy, you're stuck. And if you even some of the crazy solders that you use can do it. If I remember, I think what is it? I think it's tungsten. A lot of solders on the ground use tungsten, and I think that's what it is. Anyway, it turns out that stuff grows out. It crystallizes in some form, and it can have up to 1 to 2 inch long fibers come out of the solder, and those have been known to short out satellite wiring. In other words, if you've got a positive and a negative and a high enough potential, the solder bleeds and basically gets this hairy stuff on it that goes out and shorts out your wiring. So it's all kinds of garbage. You really got to check. This is from our Scatha satellite. This is the alpha, which is important for keeping the temperature of the satellite constant. And you can see that it changed by dramatically over 1,000 days, from down around almost 0 to over a quarter of this. See, is alpha is absorptance and epsilon is the emission, if I remember right. And so you can see that that's the way it goes. And this is another one from Scatha. This is the what kind of crud you're getting stuck on you. if you see it was negatively biased, ions typically are positively charged. I'm sorry, are negatively charged because you pulled off an electron. And so, oh no, I'm getting it backwards. Anyway, it's the bottom line is that if it's positively biased, it attracts heavy ions. If it's negatively charged, it repels negative ions. And the net result is that the spacecraft, it depends on what kind of ion it is. If it's negatively charged, it's attracted to positive surfaces. If it's positively charged, it's attracted to negative surfaces. I got it right that time. And the most heavy ions are negatively charged, and so any positively biased surface on your spacecraft is going to attract the heavy ions to them. And this is the rate at which SCAFA measured the nanograms per square centimeter per day over its mission. Conclusions. Let's see, what time are we doing? Oh, we're almost done. First of all, what's the future? Well, neutrals. We need more accurate predictions of the atmospheric density. It's really not that well known. The best way to do it is to take in situ measurements in real time from a whole vast armada of spacecraft, which is what they've starting to do. Frank Marco's pushed that concept. And from that, you can get a better idea of what the actual density is. The models can be off by a factor of 100 easily in their density, the average models. And so you need to know exactly what it is now, because it turns out that when an aurora hits, it sends out massive density waves from the auroral zone, for example. Or you saw with the ionosphere what would happen with the bias when the magnetic field. The accommodation coefficient, that needs to be better defined for the drag calculations. And every satellite is a complex combination of different surfaces and different orientations, and it rotate. They almost all rotate, and so you spin at some degree. So you have a real problem trying to figure out what the drag coefficient is, because it can change dramatically from 2 to 4, as you saw. Oxygen erosion mechanisms need to be defined. People pretty much ignore those with, if they do, they're in big trouble. The glow process is still not well defined. I haven't seen much of anything since I did my original review paper back in the 80s. And it's sort of sad. Plasmas, spacecraft charging materials are not well defined. And it turns out that when they're in space, they change over time fairly dramatically. SCAFA was a totally different satellite after a few years because of radiation damage, because of oxygen erosion, because of micrometeoroid impacts, everything. The surfaces change dramatically over time on any given satellite. There's no way to avoid that. And the net result is that what you started with is not what you finish up with. Interactions between high voltage surfaces and tethers with plasma environments are not well defined. Tethers, of course, are one of the future ways we want to try to power satellites. I've gone into that in some of my other talks, if you want to go on the YouTube. Alphane critical velocity is something we didn't discuss today. That is, apparently when you go through, if your satellite or your plasma that interacts with another plasma is going faster than the ionization velocity of the other plasma, it ionizes very effectively. And Alphane predicted that. And people just have pretty much ignored it. In other words, there's a region where you can have greatly enhanced plasma charging. And why do we care? Well, environmental effects are potentially expensive. If you lose your satellite because your silver interconnects decayed, the next time you fly, you're going to put grouting on them to keep them from decaying. And there are lots of unknowns. I mean, it's bizarre all the different things can happen. I have hundreds of case studies I can mention to you on things that have gone wrong on satellites, because I've been called in a lot of the different cases, and it's just plain ridiculous. And the proper design, however, will limit problems. If you know about these problems, like oxygen erosion, you can at least make sure that depending on how long your mission is, that you limit the number of exposed surfaces. What can you do? Well, like I said, you evaluate the mission design using my integrated approach that I recommended. You go from environments to interactions, from interactions to mitigation processes, to evaluate how the mitigation processes affect cost, schedule, and time. And finally, you build. You require adequate testing. I don't care what you're flying, you can't just fly it. And I mean, I've had everything go wrong. The night before they launched my sub-satellite on Clementine, I went to my engineer and I asked, is there an on-off switch? And he thought for a moment, he said, no. So the night before we fueled the rocket, he was out soldering an on-off switch on the damn satellite. So for God's sake, you got to think of everything. And it's just horrible. And the funniest one is one of our contractors had us come, and I gave my talk on spacecraft charging and all the things like that. So what did they decide to do? They decided to, inside the spacecraft, they put a little loop antenna, about a 2 or 3 inch loop that basically acted like a pickup antenna between every one of the ground points on the spacecraft. There were hundreds of these things when I went back to inspect what they had done. It was a total disaster. Somebody had soldered about 100 little loop antennas inside on all the circuit boards and stuff to make sure they were grounded. And the net result was that they were picking up EM pulses from everything, from everywhere. And you got to be very specific about what you tell your people to do. Do not assume they have any idea what you're talking about if it's a different field. And that's why testing is so important. During flight, you have to evaluate the effectiveness of your mitigation methodologies. It's worth it to have someone study the data that's coming back from your satellite to know, for example, what parts are failing due to radiation, what parts are having electrostatic problems and things like that. And then you need to use that data to update your models of the environment and of the interactions and of your design. So remind you, the integrated approach, identify the requirements based on the trajectory, instruments, and unique mission constraints. Rate the environments versus the interactions. Identify the design trade-offs for the most critical environment interaction concerns. Establish weight, cost, and complexity criteria. Optimize the combinations of design choices, and then evaluate the resulting design and iterate that. You can't just do without that. You have to iterate. And remind you, this is what it looks like. On the left are the environments and the interactions. Then I take the interactions and I cross-correlate those with the design options. And I take the design options and I cross-correlate those with the different design factors. And that's what I recommend. And finally, what a wise one should we do? Well, I would say concentrate on early detection, prevention, and mitigation. And what you do in the first stage of your design will be unit 1. By the time you get to building the satellite, it's going to be a factor of 10 more expensive to correct. And by the time it gets to the launch pad, you may not be able to fix it at all. So it's infinite. So the bottom line is, as early as possible, do it. Test, 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 test. Well, that's a very hard thing to get across to people. And most people don't do it because it's too expensive, it's too time consuming, and it might damage their spacecraft. And it's the might damage the spacecraft, and most people won't do it. And trust, but inspect and verify in person everything that you ask for the people to do in person. That's I've found repeatedly that the what people do has got to be backed up by a personal inspection. To give you the classic example, the whole reason spacecraft charging became a big issue was because Nixon went to China. During his visit in China, he danced with Mrs. Mao. The US used this fancy spacecraft to broadcast the discus satellites to broadcast the signal back to the US. In the middle of the dance, the spacecraft failed. It turned out that the failure was because of no one inspected the satellite at the last minute. What had happened was the spacecraft charging expert issued that all circuits needed to be grounded. One of the grounds was between the solar array system and the basic spacecraft. It required a wire to go to the spacecraft, and then the person who interpreted that was a mechanical engineer. So what he did was he drilled a hole, put a bolt on the hole, and tied a wire to ground it. Great idea. That went to the guy that actually did it. The guy that actually did it drilled the hole, wrapped the wire, and put Loctite on the bolt to make sure that it wouldn't come loose during launch. The net result was that the Loctite on each one of the spacecraft, fortunately they measured it, they found out that where more Loctite was used, it insulated the grounding bolt from the spacecraft, and that's the one that failed. The others had less Loctite, and they had no problem. So bottom line is you got to inspect. You can't trust that the poor mechanical engineer that is to actually do it knows anything about what you asked for him to do. And so utilize your mission assurance, reliability, safety, and quality assurance personnel. And finally, I have found that garlic cloves should be included in all interplanetary spacecraft just in case. So conclude with that remark. Anyway, this is some of the references, and you can see the glow paper down there. I pushed that you might want to take a look at that in 1988. And contamination, there are whole millions of papers on contamination and all the problems that they cause. And anyway, this gives you some references. And that's pretty much it. And I'm going to, there we go. Can you see me?
Yes. Very good.
I'm done. And it's,
Excellent.
so it's 3 hours. I told you it was 3 hours.
Yeah, that's wonderful. Somebody has a question. It says just thank you. It's David. Again, folks online, if you want to say something, please click raise hand. So we'll enable your microphone. VK, thank you very much for the course. So anybody want to say something? 1 second. Any question here?
I couldn't hear that.
Hello, can you hear me?
Yes.
Hi, Dr. Garrett. Thank you so much for your presentation. Found it very insightful. I have a few questions, but I'll just go ahead and ask the one for the sake of time. You mentioned that there was you worked on with JACIA, the JACIA model for the atmospheric density. But I would want to ask, so there are since then, there's been various different models for the atmospheric density.
MSIS, and but JACIA still is used by a lot of the people.
Exactly. Actually, that basically was my question is, so based on your experience, what is the recommended atmospheric model for calculating the drag area for spacecraft propagation? Is the most modern and accurate model available the MSIS 2000 by the Naval Research Academy, or is JACIA's model still using? And if so, what?
It depends. I think you need to contact either Langley or I believe actually is Marshall's probably the better one to contact. both of them have their own separate models, and I provided to them at, I believe it was at Marshall, I provided the update for the geomagnetic storm model that Yukiya wrote to them. I think I was the only person that had it. And they input that, and I think they've since revised that again. And I think they use that now. SpinVis also has several different atmospheric models in it. Have you tried SpinVis?
That's so funny you mentioned that, because that was actually my next question is what are the modern tools you recommend to perform radiation analysis for small cell?
Well, the easiest thing is to go try, if you can get in and figure it out, use SpinVis, because it has pretty much everything, even my models. So my Jovian models are like what they use. They were last time I heard they were using for radiation and stuff. But the I think that if you need the outer planets and anything like that, you need to contact JPL. I can send you who to contact. In fact, I can send you. I have it right here on my computer. I can send you the reference location website. My included my email in the very first UGraph, and so you can email me.
Perfect, thank you. So SpinVis is essentially what's used in modern spacecraft.
It's because it has everything.
Yeah.
And it's all in the same place. They don't have all the radiation models and things like that, the atmospheric models. That's JPL exclusive. And I also have a chart that I hand out. Ken, you have a chart, my chart, don't you?
You mean today's chart?
No, you have my chart of the interplanetary space. And,
Oh, yeah.
yeah, you might show that to him.
Okay.
And if he wants it, he can write me and I'll send him a copy.
Okay.
Thank you. And then I guess on the topic of SpinVis, I've done some simulations in the past for designing spacecraft.
I'm sorry, could repeat that?
So I've used SpinVis in the past for specifically to calculate the total amount of equivalent aluminum required for reducing your total ionizing dose and making sure that your mission lifetime is good enough, or you can support a certain mission lifetime given the thickness of aluminum equivalent that you're going to have on your spacecraft. But do you know of a good way to kind of account for single event upsets for modern spacecraft design?
Well, basically we use Novice in most of our calculations at JPL, and those are very detailed. There's FastRad. If you look up on the website on YouTube, one of my early talks went through all the different radiation models, and you need to ask Ken how to get to those. There are two other talks, and one of them was specifically detailed all the different radiation models and basically went over their accuracies and such. There's different kinds of ways to do it. The one way is inside out, the other is outside in, and the outside in one is much more accurate, and you use all of a sudden I forgot the name, but the Geont 4, and you use Geont 4, which is freely available, and basically you send millions of particles into the location you're interested in. The problem is that it's extremely computer intensive, whereas if you use Novice, it goes out from inside out, and as a result, you use only a tenth or a hundredth of the particles tracking, and you go backwards. But it doesn't include all the ricochets and things like that in it that Geont 4 does. So FastRad is the easiest, and it's sort of a simplified version of Novice. So those are the three codes that we usually use. Okay.
Awesome, thank you. Yeah, I've definitely explored Geont 4 a little bit in SpinVis as well. It's kind of difficult to get the current sizing, I believe, at the time I had trouble, sizing of the current day modern processors.
Okay, well, what you do, what basically, our rule of thumb at JPL is 2. You take whatever you calculate, you multiply it and divide it by 2. There's the particular reason for that is because when we flew Voyager, the project manager looked at it and he said, well, we can only afford particles that are about a factor of 2 stronger than what the radiation environment you're going to give me is. And so that's why we always pick that. But 2 is kind of a factor of 2 is kind of what we use as a cheat factor and for all the environments. The problem you have is that no matter what radiation environment model you use or anything, you don't know the environment on the day you're going to fly. And project managers love to try to use solar minimum, if you know what I mean, to use that as their design criteria. So it's just the way it is. You got to hold their feet to the fire.
Interesting. No, definitely good, very good advice. I guess now that I have you, the last question. So you've been showing the research and research of the models you've been creating for interplanetary, the different planets in the solar system. How did you go about researching and developing these atmospheric models for other planets? Did you use in situ data from planetary science satellites, or are they analytical from known parameters?
About half and half. Basically, what I did was I went through, I and my colleagues went through all the various models that we could find. We tried to pick the ones that we could reference and that were basically verifiable, that somebody actually sat down and did a calculation or did a measurement. Most of the at least the ionospheric models, are based on radio wave measurements. As JPL went by a planet, the signal would go through the ionosphere, and they would use that to try to get the ionospheric parameters. The atmospheric models, it depends on which planet you're talking about and things of that nature. As you know, we have spectrometers and things like that. We can measure some of the components of the atmosphere. And JWST certainly is starting to do that in big time, and doing that in the internal measurements for like Uranus. I know I follow Uranus quite a bit, and as far as I know, my model is the only model right now that people are using. And SatRad, my Saturn model, same thing. Jupiter, the Europeans have their own of radiation in the atmospheres and stuff like that. But they're basically a trade-off between theory and observation. And the neutral atmospheres are a little bit harder, but ionospheres, they can usually get some direct measurements as the probe flies by the planet.
Got it. Okay, thank you so much. Really appreciate it.
Any more questions?
I think Brian wanted to ask something. Brian? I think Brian.
Hi, Dr. Garrett. So I was kind of interested in the names you and the previous questioner were discussing. I was trying to Google some of those names like Spindis, GF4, but I wasn't. My Google search wasn't really coming up with much. I was wondering maybe if you could spell some of those for me.
Geant, Geant. And I think it's the version 4 right now. Maybe it's version 5, but they update it periodically. It comes out of the CERN.
Okay. And then was the other one? There was like a Spindis one, and
there was FASTRAD, FASTRAD. I think that's the Langley model.
okay.
And then there's Novice, NOVICE. That's a private venture, and if you have to look it up and pay him money.
Oh, I see. Okay, thank you.
Yeah, that's
Yeah. Also, we have a question about Michael. Michael has a question here.
Yes, hi, Dr. Garrett, can you hear me?
No, can you turn it on?
Hi, Dr. Garrett, can you hear
Yes.
me?
Yes.
Yeah, thank you for the talk. I just wanted to ask you really quickly about the, I guess in the conclusion section, you were bringing up you have like a neutral section and the plasma section. I was kind of curious about why like you did the research for these topics back in the 80s and learned more about the glow process. I was wondering, what's the reasoning behind, like, I guess, what is your best guess as to why there's so little research almost 40 years later about the same topics?
Well, the people that I worked with, I wrote the review with, our Chechen has investigated it much more thoroughly, but pretty much the conclusions didn't change all that much, if I remember. And the problem with the glow is I don't know who uses it. You got to remember that basically, if you're flying optical sensors, you don't want them to look into the rocket plumes and stuff like that for sure. And I think that the glow comes and goes. That's the other problem. It's as you can see from the data, it's very dependent on when people fire thrusters and stuff. And I think I don't know for sure, but that what you can do is you can avoid thruster firings. That's what I was pointing out. Or you go to the ones that geosynchronous orbit don't see it, and even in MEO orbit you don't see glow. It's primarily the small satellites down at low altitudes are going to be the ones that worry about it. That may be the reason that people haven't spent much time. But Ara Chechen at JPL is, as far as I know, and Dave Brinza are the two of the people that I depended on a whole lot to work those issues. You might look up Chechen and see if there are any more recent papers. But I haven't heard anything. I haven't come across it. It may be because I only look in Journal of Geophysical Research and Planetary Science, and it's a much narrower field perhaps than what other people look in. I don't know why.
Does that also turn out to like the material properties that you were mentioning? For instance, spacecraft charging, that sort of.
No, that we're doing all the time, and they're massive books. If you look at NASCAP code, they have hundreds of materials properties, and they're always measuring. JPL did an exhaustive study of several hundred materials, and the people at J.R. Dennison at Utah State is always doing studies, and on the conductivity, the properties, the spacecraft charging aspects and stuff. That whole field is they have a conference every other year on that. And the Spacecraft Interactions Conference is every other year, the opposite years, and that's run by Joe Minnow. And that for the U.S. is the main Spacecraft Environmental Interaction Conference. We used to go with AIAA, but their conferences sort of fell apart for space environments. And so nowadays there's every other year a spacecraft charging conference. I've hosted several, and then every other year the opposite year there's the Space Environment Interactions Conference, and those have all the latest work on all this stuff. But I've never seen anything on glow. The spacecraft charging is all over the place. I mean, that is the major killer of satellites. And I had a complete talk. The YouTube video on that is like, what was that, Ken? Was that the first one or the second one? I forget. But I have a complete session on that. Ken?
Yeah.
That's all the questions I have. Thank you.
Okay.
I probably will tell you over that. You know what you mentioned? We did have the space environment conference before.
Yes, they have it every other year. They just had one in over in France,
No, I mean for AIAA
Avignon in France.
only France. How about AIAA, the one you say it fell apart?
For many years, the major spacecraft charging conference was hosted by AIAA.
Oh, okay.
About 10 to 15 years ago, when they moved out of Reno, virtually everybody in space environments pulled out. I've had this discussion with the president and other people. Hastings knows all about it because he pulled out.
Oh, I see.
And just the spacecraft charging conference that they hook up with IEEE is the primary one now. So it's sponsored by IEEE. AIAA may still sponsor it, but I know that when I did it, they didn't. And I ended up having to pay for the whole damn thing.
I see.
And the French just paid for it. The Japanese were going to pay me to do theirs. So.
Okay. I'll look into this and get back to you.
No, it turns out that talked to Nelson Green, but he's on the Space Environments committee, and for AIAA, and it hasn't been successful in a number of years. They came by to JPL and talked to me about it, and I told them what to do, and they didn't do anything. So.
Yeah, I'll learn more from you about that. Also, actually, I found something. You mentioned you mentioned about this. You cannot say coating, the glass layer or thing. That reminds me because you mentioned this solar panel, the different layer of material, the structure of the device. So these days, you have a lot of semiconductor devices, and they have different packagings. They have packaging also using some kind of material. So is there any type of study, on this kind of, the scale is smaller and smaller. So is any study?
Oh no, we do that all the time. JPL is the leader in that, and as soon as people publish new parts and stuff, we try to get a hold of them. We test the hell out of them, and then we model them. And there's a whole group, about 20 people at JPL. That's all they do. We have all kinds of accelerator facilities, and the only thing you have a hard time with the heavy ions, you have to. I guess it's what Stanford is about the only place right now. I was on the National Academies board on trying to figure out how to do heavy ion testing a couple of years ago. And the bottom line is they're closing down all the facilities, or they're only doing it for medical purposes. And so, but the bottom line is that no, when parts come out, we and Goddard test the hell out of them if we can, and then my group at JPL does all the calculations of the upset rates and modeling using Geont 4 or Novice or FastRad, and we do all the calculations of the types of upsets. In fact, I've got lots of papers on that if anybody's interested in what I've done.
Yeah, I'm interested. I'll ask you more about that. So you do have a group there. They just test for all the new devices.
Yeah, they do. No, and then there's the Air Force that does a lot of testing at Albuquerque and Sandia.
Okay. My next question is because you just mentioned about MEO. So far all the like ISS, most of the mission satellite they fix on, one one altitude, or some kind of certain altitude. So suppose there's a mission, they go from different LEO, MEO to GEO. and obviously you talk about this, you have to bias, the surface, those kind of things. So do you think that will complicate a lot of the design of the spacecraft or satellite?
Well, each of the regions has its own peculiarities, and you have to address them. I mean, Geo obviously sees solar photon events and things of that nature, whereas low altitude equatorial orbits don't see much of anything. Polar orbit at low altitudes that goes from polar orbit, we'll see all kinds of solar flare events and things like that. And then you have MEO. MEO's typically in the worst parts of the radiation belts for the protons anyway, and for electrons. And so you have to consider for each orbit what the issues are. I specifically addressed this talk at low altitudes because of all the CubeSats that are going there and the concerns below 1,000 kilometers with atomic oxygen erosion and with drag and with, as I talked about, plasma interactions with the aurora.
Yeah, so it will complicate the design, right? According to what I said, because different different orbit has different kind of set of you can say danger, but consideration for.
Well, that's what I was saying. The whole point of my integrated approach was for that particular orbits that satellite's going to travel, you needed to consider all those different types of environments and interactions. And each region has a different set of interactions.
Yeah, I agree. Yeah. Yeah, this approach is very good. The integrated approach, very very important. So another question is, so far you have been talking about this is like one spacecraft or one satellite. So these days, of course, this is over time, during the mission. But these days people do a lot of ride sharing. So they launch. One launch vehicle, there are a bunch of satellites, maybe hundreds or different kind of in one payload. So they have a kind of specific kind of bus to accommodate different kind of, and may not be one type of CubeSat or one type of satellite. It could be different kind of spacecraft or component. But you have to put them all in one bus. So before they launch each of them, they will fly in space for a certain time. So do you think any of this issue consideration, for example, each of the, say, one CubeSat was designed by one company or one school and another one designed by a different group. Then you have this charging or different situation, and then you put them on the same bus. So do you think this is something that the company provide the bus need to give us certain kind of standard to each of the company design the satellite?
Well, back up for radiation, spacecraft charging, and I presume for drag calculations and stuff like that. There are specific guidelines. I've worked on for AIAA. We've generated several specific guidelines for the radiation modeling, for spacecraft charge modeling, and for the atmospheric drag models. And the AIAA issues standards on all of those. There's also international standards, ISO standards for all those things. And so people are supposed to look at those and consider them. And then what we typically do with any mission is you're supposed to have a independent review board, go over your mission design and address all the different problems that people might have. And you're supposed to have old fogies like me that know all the little bad things that can happen and to be able to discuss those during the review process. The problem you get into is people don't do reviews, and they just sort of throw things together, and the universities throw things together and then slap them on one of these things that you were talking about. One of these, everybody's going. We got to get it ready in 5 days and fly it.
Yeah, that is. Okay, so there's actually nobody, no, people just have to follow those standards, like what you say.
Well,
otherwise-
they have to have a reliability engineer that knows what standards there are that are applicable to that mission. And no one person is the key keeper, so to speak. But each program needs to have a organization that does that. Otherwise, they're bound to fail. And I mean, it's just known. And it depends on how much money you're spending. If you're only spending a few $100,000 to develop a CubeSat, you don't give a damn. If you're going to be developing a billion-dollar spacecraft like JPL does, and you've got 20 or 30 people working each one of the problems.
So you're saying basically this role is is up to each of the organizations. So there's
That's right.
nobody is going to do a overall certification for those.
No, ISO standards, AIAA standard and guidelines, and NASA has a whole bunch of guidelines and standards. I wrote the spacecraft charging standard for NASA, and that's readily available. And we just updated it about a year ago on spacecraft charging, and that has specific recommendations, specific guidelines and stuff. It's a handbook basically issued by NASA.
No, I understand, but there is no, for example, you provide the guideline, but you don't actually like give out a certification. Say you are qualified.
No, the way you do the certification is you have review boards. And NASA in particular has a review board for each mission. And there's a whole set of reviews that you have to go through from launch requirements through to the spacecraft charging requirements, radiation requirements. And we have dozens of these are required review and they're A, B, C, D phases. A is the conceptual design, B is, anyway, and then there are levels of missions. There's A, B, C, D missions, and basically you have classifications for the mission types, and each one of those missions, NASA requires certain amounts of review, certain specific reviews that you have to have. And that's all written out. It's very, very regimented procedures that you have to follow if you're doing NASA or the Air Force or DoD, and there's no getting around it.
Okay, so I see. But you just mentioned something about if somebody launches satellite very quickly and without checking all the needed standard or requirement. So how about recently this responsive space like a Victus Knox, several responsive satellite. So now you're encouraging the speed, the how the faster, the better, launch your satellite. So was something being compromised? The process you just mentioned, you have to go through.
Well, there are a lot of commercial activities going on, and basically each person, each organization picks what it thinks should be done. And I mean, you got a contract, you write a contract, and spells out how you're going to review it and do things like that for each. And if you don't, then I don't know what you can do.
You see what I'm trying to ask, right?
I know, I understand what you're saying, and what I'm saying is that as far as the commercial world is they can choose to follow or not follow the guidelines that we publish from NASA and Air Force and DoD and things like that. And different organizations have different requirements. It's impossible to try to describe all of them, but I know that NASA has very hard requirements of how you do reviews and for the given classification and mission, different class of missions.
Yeah, I think that's a dilemma. You want it very fast, responsive, but then you're
That's right. and then you have certain things that you don't do or certain things that you do. And but the basic thing is you do the reviews to make sure you're doing those phases.
Yeah, very good, very good. I understand. Yeah, I have tons of more questions, but I don't want to. Anybody online? Any question? Dr. Valentian, or anyone? Any question? Okay, if not, nobody here. So, Dr. Garrett, thank you so much. This is amazing. This is another.
You wore me out.
Sorry.
Is that how many people did you have? Just the three?
No, we have probably 7 people, 8 people in person. I think that 30 people online, but they mostly left. You know, most of it is a long. They already left by now. Yeah.
All right. All right. Well, I guess we'll see you then.
Yeah, well, this is the issue. You know, if you want to do it for 2 days, I think it's better by in person. Otherwise, people, tend to after a few
Oh, I
hours.
understand. We can discuss that some other time. Okay.
I'll work on it.
All right. It looks like there's a bunch of chats.
Oh,
I don't know what the. All right. All right. We'll see you.
yeah. See you. See you. Thank you so much.
Thank you, Dr. Garrett. Great talk.
Thank you. Let me see. Is that everybody? Yeah, I guess that is.
Yeah, a lot of people left already.